You know that moment when you're scrolling through a streaming service and it just nails the perfect movie suggestion?
Oh yeah, all the time.
Or when your phone's voice assistant actually understands your mumbled question, even when you barely finish your sentence.
It's getting scarily good sometimes.
Right. We've all seen flashes of what artificial intelligence can do. I mean, from the precision of self-driving cars, maybe, to AI systems helping doctors make critical diagnoses.
Absolutely, it's really becoming embedded.
AI is everywhere, quietly and sometimes, very overtly, weaving itself into the fabric of our daily lives. But for many, I think it still feels like this mysterious force conjuring up images straight out of science fiction.
Yeah, the sci-fi vision definitely looms large.
The reality, though, as we're about to unpack, is both more fascinating and, frankly, far more practical.
Much more grounded in engineering, really.
So today, we're going to pull back the curtain on artificial intelligence. Forget the robots for a moment. Our mission is to give you a crystal clear foundational understanding of what AI truly is, how it actually learns.
Which is the crucial part.
Exactly. And the real-world applications that are already shaping your world. We're going to try and cut through the jargon, reveal the incredible engineering behind these intelligent systems.
And what's often overlooked, I think, is that while modern AI feels incredibly cutting edge, its true intellectual roots stretch back decades. It's quite a journey.
Right, not just overnight.
Not at all. It's a journey from purely theoretical concepts and these ambitious, almost philosophical questions to the powerful engineering discipline we see today. And that shift, the shift from can machines think to can machines perform specific intelligent tasks, well, that was the psychological and pragmatic turning point that really transformed the field and unleashed its current boom.
We've got a fascinating exploration plan for you. We'll start by looking at what AI really means beyond the hype, then explore its different types.
The taxonomy is important.
Definitely. Then we'll take a deep dive into the core mechanisms of machine learning, which is truly the engine of modern AI and its distinct approaches. After that, we'll shift gears and dive into some truly impactful real-world case studies. Think about those recommendation engines.
The ones that know you better than you know yourself sometimes.
Kind of. And the virtual assistants you chat with every day, and even the complex technology behind facial recognition.
And to connect all of this to the broader landscape, we'll delve into the vital questions AI raises about our future. I mean, from how it's reshaping the economy and impacting the nature of work.
Huge questions there.
Huge.
Right.
And also how we can potentially harness its power for global good. This journey will ultimately lead us to consider a fundamental question. How do we ensure this transformative technology is built and used responsibly, benefiting everyone?
That's the big one. All right, let's get into it. #tag
Defining the landscape of artificial intelligence. #tag An introduction to artificial intelligence. So to kick things off, let's unpack this. What is AI? We hear the term thrown around constantly, but it can mean so many different things. At its broadest, sort of most academic level, artificial intelligence is this big, interdisciplinary field of computer science.
Right.
Dedicated to building machines capable of tasks that traditionally required human intelligence. And we're talking about a really wide spectrum of cognitive functions here.
Yeah, it's not just one thing.
No. AI systems are designed to reason, to learn from experience, which is huge, to understand natural language. I mean, that alone is incredibly complex for a machine.
Absolutely. Language is tricky.
To recognize intricate patterns in data, solve problems, and even make decisions, often in these dynamic, unpredictable environments. The grand vision, I suppose, is to create systems that can perceive their environment, understand it, and then take actions that maximize their chances of achieving some predefined goals. That's the ambitious academic goal, yes. But what's really crucial to understand is how AI's definition has sort of evolved in the real world, in practice.
Okay.
In the business and tech sectors, AI is often viewed far more pragmatically. It's understood more as a suite of advanced technologies, predominantly rooted in machine learning and deep learning, that enable computers to perform highly specific intelligent functions, things that were once exclusively human capabilities.
So less about consciousness, more about capability.
Exactly. So instead of thinking about sentient robots, think about how AI can identify objects in an image, seamlessly translate spoken and written language, analyze petabytes of data for hidden insights, or deliver personalized recommendations.
Right, the practical stuff we see.
Precisely. A powerful example is optical character recognition, or OCR. AI uses OCR to extract text directly from documents, turning unstructured content, like a scanned invoice, into structured, actionable data that a business can actually use. This operational definition, focusing on specific tasks, has really driven AI's commercial impact.
And what truly separates modern AI, as I understand it, from traditional computer programming is this capacity for learning and adaptation.
Right. That's the absolute key.
Conventional software operates based on explicit, meticulous, step-by-step instructions coded by a programmer. It does exactly what it's told, no more, no less.
Follows the script.
Exactly. But AI systems, on the other hand, are designed to learn and evolve directly from data. This means they can actually improve their performance over time without needing to be explicitly reprogrammed for every new scenario they encounter.
Which is a massive shift.
Huge! The fundamental principle driving modern AI is that algorithms are trained on vast amounts of data. By processing these huge data sets, the system identifies patterns, correlations, relationships, often on a scale that, well, human analytical capabilities just can't match.
We just can't see those patterns in billions of data points.
Right. And then it leverages this learned knowledge to make predictions or decisions. It's a complete flip in how we build intelligent systems.
And that flip you just mentioned is key to understanding the modern AI boom. Early AI research, it was often bogged down by these abstract philosophical questions like, can machines think?
The deep stuff.
The deep stuff, which proved incredibly difficult, almost impossible to answer definitively, and even harder to use as a foundation for building actual functional systems.
Right. How do you measure thinking?
Exactly. But by reframing the goal towards building machines that can perform specific intelligent tasks like classifying images, translating languages, or predicting stock prices, researchers created objectives that were measurable, achievable, and incredibly useful.
Oh, okay. So making it practical.
Making it practical. This pragmatic shift transformed AI from a purely academic pursuit into a powerful practical tool for solving real-world problems. This change in focus, I'd argue, more than any other single factor, truly fueled the commercial and technological explosion we've witnessed.
That makes sense.
What's also fascinating, though, and sometimes a challenge, is that this intense focus on utility has led to the development of incredibly powerful black box systems.
Yeah, the black box.
Yeah, where the internal workings and the why behind their decision-making can remain pretty opaque, even to the creators sometimes. Understanding the implications of that opacity is a challenge we're just, I think, beginning to grapple with seriously now. Hashtag, the core goals and benefits of AI.
So if we think about the goals of AI, we can maybe look at them through two lenses. The traditional, ambitious goals that guided academic research for decades, and then the very practical, tangible benefits that are driving its adoption in the real world today.
That's a good way to frame it.
On the traditional research side, AI aims to replicate kind of the full spectrum of human cognitive abilities.
Yeah.
These foundational pursuits include things like reasoning and problem solving, which is about developing algorithms that can mimic the logical deduction humans use.
Logic puzzles, that sort of thing.
Right. Then there's knowledge representation, finding ways for AI programs to store, access, and reason about facts in the real world, allowing them to answer questions intelligently.
Building a world model, essentially.
We also have planning and decision-making, creating systems that can set goals and achieve them, often by calculating the action that maximizes the best possible outcome. Learning, of course, is huge, designing programs that improve performance through experience, like we just discussed.
The core of ML.
Exactly. Natural language processing, or NLP, focusing on machines understanding, interpreting, manipulating, and generating human language. Perception involves giving machines the ability to use sensor input, like cameras and microphones, to understand the world. This covers computer vision, speech recognition.
Making sense of messy real-world data.
Yeah. And finally, the long-term aspirational goal, general intelligence, creating a machine with the flexible, adaptable intelligence of a human being, the sort of sci-fi holy grail.
The AGI dream, yeah. What's genuinely exciting, though, is how these ambitious research goals directly translate into tangible, real-world benefits that are driving the massive adoption of AI across nearly every industry today.
Okay, let's hear about those.
Firstly, there's automation. AI excels at automating both digital and physical tasks, especially those that are routine, repetitive, or what we often call dull, dirty, or dangerous for humans.
Right, the jobs nobody really wants.
Precisely. Think about automating data entry, verifying documents in a legal firm, or even the complex realm of cybersecurity threat detection. In manufacturing and logistics, robots powered by AI are doing the physical heavy lifting, freeing human workers to focus on more creative, strategic, and higher impact problems that require uniquely human skills.
So it's not just replacing, but also shifting roles.
Ideally, yes.
Yeah.
Shifting and augmenting. Secondly, AI offers an incredible leap in increased speed and accuracy. These systems can process and analyze petabytes of information that's thousands of terabytes at a scale and speed simply impossible for human teams.
Mind-boggling amounts of data.
Truly, they can sift through immense data to find subtle patterns and relationships that a person might easily miss, leading to vastly more accurate insights and predictions. This also naturally leads to a reduction of human error.
Because machines are consistent.
Exactly. Through automation and consistent algorithmic processes, AI can virtually eliminate manual errors in data processing, analytics, and even manufacturing assembly, because algorithms follow the same precisely defined processes with perfect consistency every single time. No bad days, no coffee spills on the keyboard.
Right?
Fourth, AI fundamentally provides enhanced decision-making. By offering rapid and accurate data-driven analysis, AI systems serve as incredibly powerful decision support tools. They empower organizations to make more informed, evidence-based decisions. And in some critical cases, they can even fully automate the decision-making process to respond to opportunities or threats in real time, like in high-frequency stock trading.
Super fast decisions.
Milliseconds. Fifth is 24/7 availability. Unlike human workers, AI systems aren't limited by time zones, holidays, or the need for breaks. Always on. When deployed in cloud environments, AI can be continuously working on its assigned tasks, providing constant customer service through chatbots, or monitoring vast networks for security threats around the clock. Finally, and this is a huge game changer for progress, AI is driving accelerated research and development.
How so?
Its ability to analyze massive, complex datasets quickly has dramatically sped up R&D, particularly in fields like medicine and genomics. For instance, AI has been used extensively in the predictive modeling of new pharmaceutical treatments, helping to identify promising drug candidates much faster.
Wow.
And in the incredibly complex task of quantifying the human genome, unlocking new discoveries about disease and heredity at an unprecedented pace, it's really pushing the boundaries of science.
Now, the story of artificial intelligence, it isn't a simple straight-line progression, is it? It's far more like a series of waves, these cycles of immense excitement, followed by periods of disillusionment that we often call AI winters.
It's a very accurate description, boom and bust, almost.
But then, just when things seem bleak, fundamental breakthroughs happen, often driven by a convergence of core technologies. The very idea of intelligent, non-human entities is ancient, of course, woven into mythology and early literature.
Golems and thinking statues.
Right. But the scientific pursuit of AI really kicked off in the mid-20th century.
That's a great way to put it. The intellectual groundwork, you could say, was laid even earlier in the 20th century. Think about Carol Oppek's 1921 play Rossum's Universal Robots, which actually introduced the word robot itself to the world.
I didn't know that's where it came from.
Yep. And Isaac Asimov's science fiction stories, which famously explored the ethics and societal implications of intelligent machines, giving us the 3 laws of robotics.
Which are still debated today.
Absolutely. But the first truly formal scientific proposals for AI emerged in the 1940s with Warren McCulloch and Walter Pitts's 1943 paper. They put forward this revolutionary idea that networks of artificial neurons working together could perform logical functions, a concept that, surprisingly, would become a cornerstone of artificial neural networks decades later.
Way ahead of their time. Now, here's where it gets really interesting, I think. A truly pivotal moment, a genuine paradigm shift, came in 1950. That's when British mathematician Alan Turing published his groundbreaking paper, Computing Machinery and Intelligence.
A landmark paper.
Turing wasn't really interested in that philosophical debate of can machines think. Instead, he proposed a pragmatic test he called the imitation game, now famously known as the Turing test.
Right. The test itself is quite elegant.
It is. The concept is a human interrogator types questions to both a hidden human and a hidden machine. If the machine can fool the interrogator into believing it's human based on its typed responses, it's said to have passed the test. This was revolutionary because it shifted the focus from abstractly defining thinking to evaluating a machine's ability to exhibit intelligent behavior that's indistinguishable from a human's.
A behavioral definition of intelligence, essentially.
Exactly. It provided a measurable, albeit, imperfect benchmark for the field.
And the field of AI, truly, formally began just a few years later in 1956. That's when computer scientist John McCarthy officially coined the term artificial intelligence for a summer workshop at Dartmouth College.
The Dartmouth Workshop.
That's the one. This event is widely recognized as the birth of AI as a formal academic discipline. McCarthy, along with other luminaries like Marvin Minsky, Nathaniel Rochester, and Claude Shannon, organized the workshop based on this bold, almost audacious conjecture. They basically said, every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it.
Wow, that's a strong claim for 56.
Incredibly ambitious. It set the tone for the coming decades, defining the intellectual roadmap for an entire new field.
So the next few decades saw some exciting early milestones that gave us glimpses of AI's potential. We saw Eliza, created in 1966, one of the first chatbots, designed to simulate a psychotherapist.
Which people sometimes really connected with, surprisingly.
Yeah, and Shaky, also from 1966, the first mobile robot that could actually reason about its own actions and surroundings. But despite these cool, often dazzling early creations, progress was significantly slower than the initial grand predictions, right?
Much slower. The reality was incredibly hard.
And this led to what we now understand as those AI winters periods in the 1970s and again in the late 1980s, where funding dried up and public interest kind of waned due to unfulfilled promises and the sheer difficulty of the problems being tackled.
The hype cycle took a downturn, but the field did see a significant revival in the 1980s with the emergence of expert systems.
Okay, what were those?
These were a specific form of AI designed to capture the knowledge of human experts in a very narrow, defined domain. Essentially, they encoded the expert's rules and heuristics into a program. A prime example was XCon, which Digital Equipment Corporation used to configure complex computer orders.
So very practical.
Extremely practical. It was a huge commercial success, reportedly saving the company millions annually. This was a critical turning point because it proved beyond a doubt that AI could deliver tangible, practical business value, helping to thaw out that AI winter by showing real-world utility.
Got it. And the truly modern AI boom, what we're experiencing right now, wasn't sparked by one single invention or moment, was it? You said it was more of a convergence.
Exactly. It's a powerful convergence of three foundational enablers that really changed everything and set the stage for explosive growth.
What were they?
First, massive data. The widespread adoption of the World Wide Web, starting in the early 1990s, led to an explosion of digital data. Text, images, interactions, just unbelievable amounts. This created an unprecedented, truly vast resource for training AI systems, far beyond anything researchers had access to before.
The fuel for the fire.
The fuel, absolutely.
Yeah.
Second, computational power. We saw the development of incredibly powerful processors, especially graphics processing units, or GPUs.
From gaming, right?
Exactly. Originally designed for the parallel processing demands of video games, but it turned out they were perfectly suited for the parallel computations needed to train complex AI models, especially neural networks.
A happy accident.
A very happy accident for AI. And third, algorithmic breakthroughs. Key algorithms, like backpropagation, which allows neural networks to learn effectively, became much more prominent and refined. This allowed these deep neural networks to actually learn from data more efficiently and effectively than ever before.
Data, power, and better math, essentially.
That's a good summary. This convergence really powered a new statistical approach to AI, where machines learn directly from data, rather than being explicitly programmed with fixed rules. This shift was vividly showcased in a series of high-profile victories that captured public attention.
Like Deep Blue.
Right. In 1997, IBM's Deep Blue supercomputer famously defeated world chess champion Garry Kasparov, demonstrating the sheer power of brute force computation and search. Then, in 2011, IBM's Watson won the quiz show Jeopardy!
I remember that. That was amazing.
It was. It showcased its advanced ability to understand and process the incredible nuances and ambiguities of human language, which was a huge leap forward for natural language processing.
But perhaps the most crucial milestone of this entire modern era, the one that truly kickstarted the current revolution, happened in 2012. Is that right?
I would argue so. That's when a deep learning model called AlexNet achieved a breakthrough victory in the ImageNet Image Recognition Challenge.
ImageNet, okay.
Its performance was so incredibly superior, so far beyond traditional methods, that it truly ignited what we now call the deep learning revolution. This demonstrated the immense, almost magical power of deep neural networks to handle complex, unstructured data-like images.
So that was the turning point for deep learning.
It really put it on the map and made everyone pay attention. And it fundamentally set the stage for the modern AI landscape, including the incredibly rapid rise of generative AI and large language models, or LLMs, that are dominating headlines today.
The GPTs and all that.
Exactly. So just to quickly summarize these key milestones and their significance, giving you kind of roadmap of AI's evolution, you have the Turing test in 1950, shifting focus to intelligent behavior. The Dartmouth workshop in 1956, formally establishing AI as a field. ELIZA in 1966, an early fascinating demo of NLP. The rise of expert systems in the 1980s, proving AI's commercial value. IBM's Deep Blue in 1997, showcasing computational power. IBM's Watson in 2011, highlighting language processing advances. AlexNet in 2012, igniting the deep learning revolution.
Now is the big one.
A huge one. And finally, the era from roughly 2018 to the present, defined by the explosion of generative AI and large language models, bringing human-like text generation and other capabilities to a global audience. Each of these moments wasn't just a technical achievement. It was a conceptual leap that pushed the boundaries of what we thought machines could do. Hashtag ###B, a taxonomy of intelligent systems.
So as you can probably tell from that history, the term artificial intelligence is really broad. It covers everything from, I don't know, the simple algorithms tucked away in your smartphone to the sentient robots we imagine in science fiction.
It's a huge umbrella term.
It is. So to make sense of this vast, often confusing landscape, it's incredibly helpful to categorize AI systems based on their capabilities. This helps us clearly distinguish between the AI that actually exists today and the more advanced, often hypothetical forms that are still just theoretical.
Absolutely. Clarity here is key. The most common way to classify AI is by its level of intelligence and flexibility, typically divided into three main categories. And this really highlights the profound gap between today's practical AI and the aspirational AI of the future.
Okay, what are the three?
The first category is artificial narrow intelligence, ANI, often called weak AI. This is the only form of artificial intelligence that has been successfully realized to date.
So this is what we have now.
This is what we have now. It drives nearly all the AI we interact with every day. ANI systems are designed and trained to perform a single specific task, or maybe a very limited range of related tasks.
Like playing chess or identifying spam?
Exactly. While they can often achieve superhuman performance within their specialized domain, like a program that beats the world's best chess players, or an algorithm that detects fraudulent transactions more accurately than a human, they completely lack the ability to generalize their knowledge to other unrelated domains.
So the chess program can't drive a car.
Precisely. A Go player can't drive a car, and your voice assistant cannot compose a symphony. Its intelligence is narrowly focused.
Gotcha.
Examples of narrow AI are truly ubiquitous in our modern lives. They include the voice assistants you use daily, like Siri or Alexa, specialized for voice commands. Recommendation engines on platforms like Netflix and Amazon are ANI, designed to predict your preferences. Your email's spam filters are ANI. Even complex systems like facial recognition systems and the AI brains in self-driving cars, despite their intricate operation, fall under ANI because their intelligence is confined to those specific domains.
Okay, so that's narrow AI. What's next?
The second category is artificial general intelligence, AGI, sometimes referred to as strong AI. This is a purely theoretical form of AI that does not yet exist.
The sci-fi dream again?
Pretty much.
Yeah.
AGI would possess the full capacity to understand, learn, and apply its intelligence to solve any intellectual task that a human being can. It would exhibit the flexibility, adaptability, and common-sense reasoning that is characteristic of the human mind.
So it could learn medicine and then apply it to finance.
Exactly. An AGI system could seamlessly transfer knowledge from one domain to another, taking insights from medical literature and applying them to financial analysis, for example. It remains the ambitious long-term goal for many researchers and represents a machine with an intelligence equivalent to our own, potentially even including consciousness and self-awareness. But again, purely theoretical right now.
And the third category?
The third category is artificial superintelligence, ASI. This is a hypothetical future stage of AI that would dramatically surpass human intelligence across virtually every domain imaginable.
Beyond human level.
Way beyond. We're talking about capabilities far beyond human comprehension, including scientific creativity, general wisdom, maybe even social skills far exceeding ours. An ASI wouldn't just be faster or more efficient than a human mind, it would be capable of cognitive feats that are qualitatively beyond our current understanding.
That sounds Intense.
It's highly speculative, absolutely.
Hmm.
And it's the subject of intense debate among futurists and researchers, raising profound questions about the future of humanity if it ever came to pass.
So what this really boils down to, it seems, is a key tension in the modern AI landscape. The practical, undeniable successes of narrow AI that we use every day
Right, the stuff that works.
versus the distant promise, and let's be honest, often exaggerated peril of AGI or ASI.
That's the dichotomy.
The incredible breakthroughs and valuable business solutions delivered by narrow AI today are fueling massive investment and the rapid progress we see all around us. But simultaneously, the distant promise and sometimes the feels of artificial general intelligence are what drive a lot of the public discourse and the most ambitious long-term research agendas.
They capture the imagination.
They do. And this duality often means that public perception of AI is heavily shaped by science fiction's dramatic portrayals of AGI, which can lead to both inflated fears about what today's AI systems are truly capable of, and frankly, unrealistic expectations. It's a critical distinction to keep in mind.
Another incredibly useful way to classify AI, beyond just raw capability, is by its functionality. This describes precisely how a system processes information and interacts with its environment. This framework, often attributed to researcher Aaron Hintz, outlines 4 distinct types of AI.
Okay.
You can think of it as an evolutionary path, almost. Each stage builds upon the capabilities of the previous one, offering a roadmap of the core challenges in AI research.
So like levels of complexity.
Exactly. Type I reactive machines. This is the most basic and, in many ways, the oldest type of AI. Reactive machines are designed purely to respond to specific stimuli based on pre-programmed rules. Critically, they have absolutely no memory of past events.
No memory at all.
None. They cannot use past experiences to inform their current decisions. They perceive the world directly, act on what they see in that very moment, and given the exact same input, a reactive machine will always produce the same output. Predictable.
Okay, like Deep Blue.
That's the classic example. IBM's Deep Blue, the chess-playing supercomputer. Deep Blue could identify all the pieces on the chessboard and calculate the optimal next move from millions of possibilities, but it had no memory of previous moves within that game, let alone any past games that it ever played. It was purely reacting to the current state of the board.
Just the here and now.
Just the here and now. Many modern spam filters also operate on similar reactive principles, simply classifying based on immediate input and predefined characteristics of the email.
Got it. Type 1 reactive. Let's type 2.
Type 2, limited memory. This category encompasses the vast majority of AI systems in use today. Limited memory machines build upon the reactive principles by adding a crucial capability: the ability to store and use historical data temporarily to improve their performance over time.
Okay, so they do have some memory.
They do, but it's limited. The knowledge they gain from past data is temporary and is primarily used to inform immediate decisions, not to build a generalized long-term memory or understanding of the world. This is the foundational capability that enables most machine learning models we use.
Like self-driving cars.
Perfect example. A self-driving car uses its sensors to observe the speed and direction of other vehicles, traffic signals, lane markings. This specific information isn't stored permanently, but it's used in real time and temporarily added to the car's pre-programmed representation of the world. This allows the car to make safe and effective driving decisions, like when to change lanes or brake, based on these recent observations.
So it remembers this car that just passed it, but maybe not from yesterday.
Exactly. Customer service chatbots that learn from past interactions within a single conversation to provide better answers are another good illustration. The memory is short-term, tasks-specific.
So, with limited memory, we really start to see AI move beyond simple, immediate reactions into something more dynamic, capable of retaining some context. Where does that progression take us next in terms of AI's capabilities? What's type 3?
Exactly. And that leads us to type 3, theory of mind. Now, this is a more advanced, future class of AI that crucially does not yet exist.
Still theoretical.
Still theoretical. Theory of mind AI would represent a significant leap forward because these machines would be capable of understanding and modeling the mental states of other intelligent beings.
Like understanding thoughts and emotions.
Precisely. They would possess a form of social and emotional intelligence, recognizing that humans and other agents have thoughts, emotions, beliefs, and intentions that profoundly affect their behavior. Such an AI could, in theory, adjust its own behavior in complex social interactions, potentially leading to truly collaborative and empathetic human-machine partnerships.
Wow, that's a big jump.
It's a huge jump. While this remains theoretical, early research into artificial emotional intelligence is beginning to explore this frontier. The transition from limited memory AI to theory of mind AI is one of the most significant, still unsolved challenges in the field. It requires moving beyond simple data patterns to truly modeling complex, unobservable states like belief and desire. That's hard.
I can imagine. And type 4.
And finally, type 4, self-awareness. This is the most hypothetical stage of AI development, truly the realm of science fiction at this point.
Consciousness in machines.
Essentially, yes. A self-aware AI would possess its own consciousness, a profound sense of self, and a deep understanding of its own internal states, needs, and desires. It wouldn't just be able to understand the emotions of others, like in theory of mind AI, but it would also possess its own emotions, internal motivations, and a subjective experience of the world. This represents the theoretical pinnacle of AI evolution, where a machine would have an intelligence and consciousness indistinguishable from, or perhaps even superior to, a human's.
Okay, definitely sci-fi for now.
Definitely. So this functional taxonomy, these 4 types, it's more than just a way to classify. It serves as a powerful roadmap of capabilities. It clearly illustrates the progression of AI, from simple stimulus response in reactive machines to data-driven learning in limited memory systems, and then onwards toward the immense, still unsolved challenges of social reasoning and ultimately consciousness.
Right.
It really helps explain why today's AI, despite its incredible power, is still fundamentally limited to complex pattern recognition, and why the leap to truly human-like intelligence remains a distant aspirational goal. #2, the mechanisms of machine learning.
Okay, now that we've got a handle on what AI broadly is and its different forms, let's talk about machine learning, or ML. You said this is really the engine of modern AI.
It absolutely is, the driving force.
It represents a fundamental shift from the old way of explicit programming, where you tell a computer exactly what to do, step by step.
A traditional recipe.
Right. To a new paradigm of learning directly from data. It's been a game changer, but what exactly does learning from data mean for a machine? How does that work?
That's a great question to frame it. Machine learning is a core subset or branch of AI. It's specifically focused on the development and study of statistical algorithms that enable computer systems to progressively improve their performance on a specific task by learning from data, all without being explicitly programmed for every single scenario.
So less hand coding of rules.
Much less. Instead of a human programmer meticulously writing detailed step-by-step rules for every possible input, the programmer essentially provides a learning algorithm and a large data set. The system then takes this data and infers its own rules, patterns, and insights from it.
Okay.
It's like teaching a child by showing them hundreds of examples of cats, rather than giving them a precise instruction manual defining catness. The system learns the defining features itself.
And this learning process, this learning paradigm I read, can be understood as a cycle involving 3 core components.
That's a good way to think about it, yeah. First, there's a decision process. This is where the algorithm makes a prediction or a classification based on the input data it receives. For example, if you feed it an image, it might predict whether that image contains a cat.
Makes a guess.
Makes an educated guess based on its training. Second, there's an error function. After making a prediction, the algorithm evaluates how good that prediction was. If the training data is labeled, meaning it includes the correct answers, the error function measures the discrepancy, the gap, between what the model predicted and what the correct outcome actually was. How wrong was it?
Measures the mistake.
Exactly. And third, and critically, there's a model optimization process. Based on that calculated error, the algorithm systematically adjusts its internal parameters, which are often called weights. The goal of these adjustments is to reduce that error. This iterative evaluate and optimize cycle is repeated thousands, sometimes even millions of times, with the model getting progressively more accurate with each iteration until it reaches a desired level of performance. It's truly a process of continuous self-correction guided by the data.
Okay, AI, ML, deep learning.
Yeah.
People use these terms interchangeably sometimes. Can you clarify the relationship?
Yeah, that causes a lot of confusion.
Yeah.
It's crucial to understand they describe a hierarchical relationship, like nested Russian dolls.
Okay.
Artificial intelligence, AI, is the all-encompassing concept, the big umbrella, of creating machines that can simulate human intelligence and behavior. It's the broad field that includes everything from early rule-based systems to today's data-driven methods.
The whole idea.
The whole idea. Machine learning, ML, then, is a subset of AI. It's a specific approach to achieve AI that's based on the idea that systems can learn from data, identify patterns, and make decisions with minimal human intervention. It's one way to do AI.
A technique within AI.
Exactly. And finally, deep learning, DL, is a specialized subfield of machine learning. It's a particular technique for implementing ML that uses multi-layered artificial neural networks to learn from vast amounts of data.
So AI is the goal, ML is a method, and DL is a specific technique within ML using neural networks.
You got it. And when we talk about artificial neural networks, ANNs, these are the algorithms that truly form the backbone of deep learning. The depth in deep learning, as you might guess, refers to the number of layers in these neural networks.
More layers deeper.
Generally, yes.
Okay.
This conceptual evolution from early AI, often rule-based,
Delays.
to statistical limited rules, to DL, which learns even the representations of the data itself, automating feature extraction is key. This progression has made models incredibly powerful and autonomous. But also, as you hinted at earlier, sometimes more complex and opaque. That's where the black box problem really comes in, leading to the growing need for explainable AI, or XAI, which we'll definitely circle back to. Hashtag 3 core models of machine learning. Machine learning systems are typically categorized into 3 primary paradigms based on the nature of the data they use and their learning method. These are supervised learning, unsupervised learning, and reinforcement learning.
The big 3.
The big 3. Each paradigm is suited to different types of problems and represents a distinct approach to extracting knowledge from data.
Okay, let's break them down.
First, supervised learning. The core idea here is learning with a teacher, or from examples where the correct answers are already known. It uses labeled data, that means input data paired with its corresponding correct output. The goal is to predict a specific output or outcome.
Like the student with the answer key.
Exactly that analogy. Common algorithms here include things like linear logistic regression, decision trees, support vector machines, lots of classic ML techniques.
Got it. Labeled data, predict outputs. What's next?
Second, unsupervised learning. In this paradigm, the core idea is to discover hidden structures and patterns in data entirely on its own, without any prior knowledge of the answers. It uses unlabeled data, just the raw input, without any corresponding outputs.
No answer key this time.
No answer key. The goal is to understand the inherent structure of the data, or to group similar items together. It's like giving a detective a huge pile of documents and asking them to find connections without telling them what they're looking for.
Finding the patterns yourself.
Exactly. Common algorithms here include k-means clustering, principal component analysis for dimensionality reduction, and association rules, like market basket analysis.
Okay. Unlabeled data, find structure. And the third one?
And third, reinforcement learning. This is a distinct paradigm where the core idea is to learn through trial and error by dynamically interacting with an environment. It doesn't use predefined data in the traditional sense. Instead, the agent generates data through its actions within the environment.
Learning by doing.
Learning by doing. Precisely. The goal is to learn a sequence of actions to maximize a cumulative reward over the long run. It's like training a dog with treats for good behavior, positive reinforcement for desired actions.
So learning through feedback.
Through feedback, yes. Rewards and penalties. Common algorithms for reinforcement learning include Q-learning, SARSA, and deep Q networks, which combines deep learning with RL. This overview sets the stage for a deeper dive into each of these fascinating approaches.
Let's start with supervised learning then. You said this is arguably the most common and straightforward paradigm in machine learning.
Yeah, it's probably the most widely used in industry today.
And it's behind so many of the AI applications you encounter every day. The defining characteristic here is its use of labeled data to train models that can then make accurate predictions about new, unseen data.
Right. The supervision comes from those labels.
Like a student studying for an exam. They have practice problems with an answer key, and they learn the material by seeing the correct solutions.
That's a very apt analogy. The methodology is precisely that. The machine learning algorithm is trained on a labeled data set. This means that for every data point in the training set, there's a corresponding correct output or label that serves as the ground truth.
A right answer.
The right answer. The primary goal of the algorithm is to learn the underlying mapping function, essentially, the hidden rules that connect the input features to that correct output label. By analyzing thousands or even millions of these input-output examples, the model slowly learns the patterns and relationships within the data.
Okay.
Once this training is complete, the model can then be used to make predictions on new, unlabeled data where the output is unknown. It generalizes from the examples it saw. Hashtag classification versus regression.
Now, supervised learning problems typically fall into 2 main categories, and the distinction is all about the type of output the model is trained to predict. First, there's classification. In classification, the goal is to predict a discrete, categorical label. So the output of a classification model is a specific class or a category to which the input data belongs, putting things in buckets.
Stuffing labels, yeah.
For example, classifying an email as either spam or not spam, that's a classic classification problem. Or in image recognition, identifying if an image contains a cat, a dog, or a bird.
Object recognition.
Right. In medical diagnosis, it could be predicting whether a tumor is malignant or benign based on medical imaging results. And then there's sentiment analysis, where you determine if a customer review expresses positive, negative, or neutral sentiment. These are all about putting data into distinct buckets.
And to evaluate how well these classification models perform, we use specific metrics. The most common include accuracy, which is simply the proportion of correct predictions overall.
How often it's right.
Yep. But sometimes accuracy isn't enough, especially if your classes are imbalanced. So we also look at precision, which measures how many of the items we predicted as positive were actually positive.
Avoids false alarms.
Right. And recall, which measures how many of the actual positive items we correctly identified.
Catches everything it should.
Exactly. The F1 score is the harmonic mean of precision and recall, offering a balance between the two. And a confusion matrix is also often used to visualize performance, breaking down the true positives, true negatives, false positives, and false negatives. It gives you a detailed picture.
Okay, so that's classification predicting categories. What's the other type?
The second type is regression. With regression, the goal is to predict a continuous numerical value. So instead of assigning a category, a regression model outputs a quantity, a number on a spectrum.
Like predicting a price.
Exactly. Predicting the price of a house based on features like its square footage, number of bedrooms, location, that's a classic regression problem, or forecasting the future price of a stock.
Predicting numbers.
Predicting numbers. Another good example is weather forecasting, like predicting tomorrow's exact temperature in degrees Celsius or Fahrenheit, or the amount of rainfall in millimeters.
Got it.
For regression models, we evaluate their performance based on how close their numerical predictions are to the actual values. Common metrics include mean squared error, MSE, which heavily penalizes larger errors because it squares the difference.
Big mistakes hurt more.
Right. Root mean squared error, RMSE, puts the error back on the original scale, which is often more interpretable. Absolute error, MAE, just averages the absolute differences, so it's less sensitive to outliers. And R-squared measures the proportion of variance in the dependent variable that is predictable from the independent variables. Kind of like how much of the change does the model explain.
Okay.
What's often crucial here, and sometimes surprising, is the no free lunch theorem in machine learning.
Sounds intriguing.
It basically states that no single algorithm is inherently best for every single problem. Model selection is always a process of trade-offs. For instance, a highly interpretable white box model, like a decision tree.
You can see how it works.
Exactly, you can follow the logic. That might be preferred in regulated industries like finance or healthcare, where explaining why a decision was made is as critical as its accuracy. Conversely, a more complex black box model, like a neural network.
Harder to peek inside.
Much harder. But it might be chosen for a task like image recognition, where raw predictive power is the primary concern, even if it means sacrificing some interpretability. This constant trade-off between performance, interpretability, and computational cost is a central consideration for any machine learning practitioner. There's no magic bullet algorithm.
Let's do a quick algorithm deep dive into the decision tree. You mentioned it as a white box model. It sounds pretty fundamental.
It is. It's a foundational supervised learning algorithm, and it's truly notable for its simplicity and, importantly, its interpretability. It can be used for both classification and regression tasks, and it serves as a fundamental building block for more complex ensemble methods, like random forests.
Okay, so how does it actually work? What does it look like?
The structure of a decision tree is incredibly intuitive. It's hierarchical and flowchart-like, very much mimicking human decision-making processes.
Like a game of 20 questions.
A bit like that, yeah. It consists of a root node at the very top, which represents the entire data set and is the starting point for splits. From there, you have internal nodes, also called decision nodes. Each internal node represents a test on a specific feature, like asking, is age greater than 30?
A yes/no question.
Usually, yeah.
Yeah.
Then you have branches extending from each node, which represent the possible outcomes of that test, such as yes or no. Finally, at the end of these branches, you find the leaf nodes, or terminal nodes. These are the final outcomes, either a class label for classification tasks, spam or not spam, or a continuous value for a regression task like $50,000.
Okay, so it's a series of questions leading to an answer. How does it decide which questions to ask?
Good question. For classification, the algorithm builds the tree by recursively splitting the data. At each node, its goal is to find the feature and the specific split point, like age 30 versus ages 30, that will result in the purest possible child nodes.
Purest, meaning?
Purity, in this context, means how homogeneous the data in a node is with respect to the class labels ideally. A leaf node would contain data points from only a single class. So they're classifying spam. You want a leaf node that's all spam emails, or all not spam emails.
Makes sense.
To make these splitting decisions, algorithms use mathematical criteria like information gain, based on a concept called entropy, which measures disorder, or gene impurity. The core idea is to choose the split that creates the most organized single-class groups of data at each step, maximizing the information gained or minimizing the impurity.
Okay, that's for classification. How about regression, predicting numbers?
When it comes to regression, a regression tree operates on a very similar splitting principle, but its ultimate goal is to predict a continuous value. So the leaf nodes in a regression tree won't contain a class label, but rather a predicted numerical value, which is typically the mean average of the training samples that fall into that specific leaf.
So everyone in that leaf gets the same predicted price, for example.
Exactly. The splitting criterion is different too. Instead of minimizing impurity, the algorithm aims to minimize the variance, or more commonly, the mean squared error, MSE, of the data points in the resulting child nodes. This ensures the predicted numerical value is as close as possible on average to the actual values in that leaf.
Got it. So what are the pros and cons? You said it's interpretable.
That's the biggest pro. Decision trees are a white box model. Their logic is transparent, easy to visualize, and can be explained to non-experts, which is a huge advantage in many real-world applications where understanding the why is critical, like in credit scoring or medical diagnostics. They also require relatively little data preparation compared to other algorithms.
But there must be downsides.
Oh, definitely. Their main drawback is a strong tendency to overfit the training data.
Meaning it learns the training data too well.
Exactly. It becomes overly complex, essentially learning the noise and specific quirks in the training data rather than the underlying generalizable signal. This results in very poor performance on new, unseen data it hasn't encountered before. They can also be unstable. Small variations in the training data can sometimes lead to a completely different tree structure being learned, which can be frustrating.
So how do people deal with that overfitting problem?
These issues with overfitting and instability are often addressed through specific techniques. One common approach is pruning, where you essentially remove branches from the tree after it's built branches that are providing little or no real predictive power on validation data. This makes the tree simpler and more robust.
Trimming the tree.
Pretty much. But an even more powerful solution involves using ensemble models, like the popular random forest algorithm. A random forest actually builds and then averages the predictions of many, many individual decision trees, each trained on slightly different data or features.
Wisdom of the crowd, but for trees.
Exactly. Averaging across many trees significantly increases robustness and accuracy and really helps to mitigate that overfitting problem. It's a fantastic example of how combining simpler, less stable models can lead to a much more powerful and reliable one overall.
Okay, now let's shift gears and pivot to unsupervised learning. This sounds quite different from supervised learning because it operates on data that has not been labeled with correct outcomes.
That's the key difference. No labels, no teacher.
Instead, its goal is much more exploratory, to analyze unlabeled data and discover hidden patterns, structures, and relationships within it, all without any human guidance on what to look for.
Right. It's about letting the data speak for itself.
It's like being handed a massive, unorganized library and being asked to find natural categories of books without any pre-existing labels like fiction or history.
That's a perfect way to put it. In an unsupervised learning scenario, the algorithm is given a data set that consists only of input features, with no corresponding output labels. The system's objective isn't to predict a specific known value, but rather to understand the data's intrinsic structure. It works by identifying similarities and differences among the data points and then organizing them based on these newly discovered properties.
So what kind of tasks is this good for?
This makes unsupervised learning particularly well suited for tasks where the goal is to gain a deeper understanding of the data itself. Common applications include exploratory data analysis, EDA, where you uncover initial insights in a new data set you don't know much about. It's also vital for customer segmentation.
Grouping customers.
Exactly. Grouping customers into distinct segments based on their behaviors or demographics for targeted marketing. Another key application is anomaly detection, identifying unusual data points that deviate significantly from normal behavior.
Like finding fraud.
Precisely. Finding fraud in banking transactions or spotting defects on a manufacturing assembly line. And finally, dimensionality reduction, which is about simplifying a data set by reducing the number of input features while still retaining its essential structure. This can help speed up other machine learning processes or make data easier to visualize. Hashtag clustering versus association.
Within unsupervised learning, two of the most common tasks seem to be clustering and association rule mining. Let's break down clustering first.
Okay.
This is the task of grouping a set of data points in such a way that points within the same group, which we call a cluster, are more similar to each other than they are to points in other clusters.
Finding natural groups in the data.
And that idea of similarity is based on some kind of distance metric, usually calculated from the features of the data points.
That's right. Often Euclidean distance, the straight line distance, but other metrics can be used depending on the data.
For example, imagine a large retail company trying to understand its customer base better. They could use clustering to analyze their customer purchase histories. The algorithm might identify distinct groups of customers.
Without being told what groups to look for.
Right. Perhaps one group that consistently buys high-value items but infrequently. Another group that makes many small, frequent purchases, and maybe a third group that primarily buys items only when they are on sale.
Finding those behavioral segments.
Exactly. Once these distinct customer segments are identified, the company can then target each group with different, highly customized marketing strategies. It's about finding natural divisions in your data that aren't immediately obvious just by looking at it.
Then there's association rule mining. This technique is used to discover interesting if-then relationships between variables within very large data sets. These rules help identify items that frequently co-occur.
The classic people who buy diapers also buy beer example.
That's the apocryphal story, yes. But the classic application is definitely what's known as market basket analysis in retail. A retailer analyzes transaction data to find products that are often bought together. An association rule might look like bread, peanut butter, jelly.
If bread and peanut butter are in the basket, jelly is likely too.
Exactly. This rule means that if a customer buys bread and peanut butter, they are also likely to buy jelly. These rules come with metrics like support, which tells you how often these items appear together in all transactions, how common is the pattern, and confidence, which is the probability of a customer buying jelly given that they have already bought bread and peanut butter. How reliable is the rule?
Okay.
These insights are invaluable for things like optimizing store layout, put related items near each other, designing cross-selling promotions, customers who bought this also bought, and creating product bundles. It helps businesses understand customer purchasing habits at a deeper level.
What's often surprising about these unsupervised techniques is their crucial connection back to supervised learning. While supervised learning drives many of the predictive applications we see, unsupervised techniques are often a critical precursor, laying fundamental groundwork.
That's a really important point. They often work together.
Think about it. Before a business can build a highly effective model to predict which customers will churn, which is a supervised task, predicting a label, churn or not churn, it often first uses clustering, an unsupervised task, to understand what distinct types of customers it actually has.
Segmenting before predicting.
Right. This deep understanding of the data's natural groupings derived from unsupervised learning is foundational. It allows for much more targeted and effective feature engineering and model building in subsequent supervised learning stages. In fact, the insights generated by unsupervised learning can even redefine the business problem itself by revealing previously unknown market segments or data patterns that weren't obvious to human analysis. It helps you ask better questions. Let's do a deep dive into one of the most popular and, I gather, efficient clustering algorithms. K-means clustering.
Yes, K-means is definitely a workhorse in the unsupervised learning toolbox. It's a centroid-based algorithm.
Meaning it uses a central point for each cluster.
Exactly. It represents each cluster by a single central point, or centroid. Its objective is to partition a dataset into distinct, non-overlapping clusters. The algorithm's primary goal is to minimize the within-cluster sum of squares, WCSS, which is also known as inertia.
Okay, WCSS or inertia, what does that measure?
It's a measure of how internally coherent or tight the clusters are. It's calculated by summing the squared distances between each data point and the centroid of its assigned cluster. A lower WCSS value indicates that the data points are, on average, closer to their cluster center, resulting in denser, more compact clusters. You want low inertia.
Got it. Tighter clusters are better. How does k-means actually find these clusters?
K-means works through an iterative process of assigning data points to clusters and then updating the cluster centroids. It goes like this.
The user must first specify k, which is the number of clusters they want to find in the data. This is a critical hyperparameter that needs to be decided in advance. How many groups are you looking for?
You have to guess K up front.
You do. That's one of its challenges.
Mm.
Step 2. The algorithm initializes the centroids. A common method is to randomly choose k data points from the dataset itself to serve as the starting cluster centers.
Plunks down some starting points.
Right. Step 3. This is the assignment step. Each data point in the dataset is assigned to the cluster whose centroid is the nearest. Nearness is typically measured using Euclidean distance, the straight line distance. This step effectively partitions the entire dataset into k-clusters based on proximity to the current centroids.
Everything gets assigned to its closest center.
Correct. Step 4. This is the update step. After all points have been assigned to a cluster, the centroid for each of the k-clusters is recalculated. The new centroid for a cluster is simply the mean average position of all the data points that currently belong to that cluster.
So the center moves to the middle of its assigned points.
Exactly. It repositions itself to better represent its members. Step 5. Steps 3 and 4 are repeated. In each iteration, data points might get reassigned to a different cluster if they are now closer to a newly updated centroid, and the centroids will shift their position based on their new cluster members.
Assign update, assign update.
Exactly. This process continues until the cluster assignments no longer change significantly from one iteration to the next, or the centroids barely move. At this point, the algorithm is said to have converged, finding a stable set of clusters.
Okay, that sounds fairly straightforward.
Yeah.
But you mentioned challenges. Guessing K was one.
Guessing K is a big one. Another is that its performance can be sensitive to the initial random placement of those centroids. A poor initialization can lead to suboptimal clustering results. You might end up with clusters that don't quite make sense or capture the real structure.
So the random start matters.
It can matter a lot. To get around this, it's common practice to run the algorithm multiple times with different random initializations and then choose the result that yielded the lowest WCSS, indicating the best clustering found across the runs.
Run it a few times, pick the best.
Right. And for determining the optimal number of clusters, that critical k-value techniques like the elbow method are often used. You plot the WCSS for different values of k, e.g. k2, k3, k equals 4, and look for an elbow point in the graph where the rate of decrease in WCSS sharply slows down.
For adding more clusters doesn't help much anymore.
Exactly. That point often suggests a reasonable value for k. But it's not always a crystal clear elbow. It often requires some judgment.
Let's move to the third major paradigm, reinforcement learning, or RL. This sounds quite distinct from learning from static data, whether it's labeled or unlabeled.
It is very different. The learning process itself is dynamic.
Instead, reinforcement learning is all about making optimal decisions through dynamic, continuous interaction with an environment. It's almost like teaching a child to ride a bike through trial and error, offering encouragement when they balance and correcting when they fall.
That's a good analogy, learning by doing and getting feedback.
But on a much more complex scale, I assume.
Oh yes, reinforcement learning is fundamentally a goal-oriented learning process based on trial and error. The framework involves several key components. First, there's the agent.
The learner.
The learner, or the decision maker. This could be a robot navigating a room, a software program playing a game like Go or chess, or an algorithm managing an investment portfolio. Second, we have the environment, which is the external world in which the agent operates. The agent's actions cause changes in the state of this environment.
The world it lives in.
Correct. Third, we have the state, which is a snapshot of the environment at a particular moment in time containing all the relevant information the agent needs to make a decision, like the positions of all pieces on a chessboard. Fourth, the action A is a move or decision that the agent can make from a given state. And fifth, the reward.
Feedback.
The numerical feedback signal the environment provides to the agent after it takes an action. Rewards can be positive, reinforcing desired behavior, +1 for winning a game, or negative, acting as a penalty to discourage certain actions, -1 for crashing the robot.
Okay, agent, environment, state, action, reward. And this is the crucial distinction, right? Reinforcement learning isn't about finding a single correct action for a given state, like in supervised learning.
Not directly, no.
Instead, it's all about the long-term consequences of actions. The agent's objective is to learn a policy. What's that?
The policy is essentially the agent's strategy or a mapping from states to actions. It tells the agent which action to take in any given state. And the optimal policy is the one that maximizes its cumulative reward over the long run.
Not just the immediate reward.
Not just the immediate reward, but the total reward accumulated over many steps, potentially into the distant future. It's about learning sequences of decisions that, over time, lead to the greatest total reward. It's a fascinating challenge, especially when rewards might be delayed. You make a move in chess now, but the reward, winning the game, might only come 50 moves later.
How does it learn that connection?
That's the core challenge. A central and very human-like challenge in reinforcement learning is the exploration-exploitation trade-off.
Explore versus exploit. Heard that before.
Right. The agent must constantly balance two competing goals. On one hand, it needs to exploit its existing knowledge by taking actions that it already knows or thinks it knows will lead to good rewards sticking with what works.
Play the best move it knows.
On the other hand, it needs to explore new, untried actions to potentially discover even better rewards that could lead to a superior overall policy trying something new, even if it looks risky initially.
Maybe a sacrifice in chess leads to a win later.
Exactly. If it exploits too much, it might get stuck in a suboptimal strategy, never finding the true best path. If it explores too much, it might fail to capitalize on what it has already learned and take unnecessary risks or just flail around. Finding that balance is critical.
Tricky balance.
Very. This entire process is often modeled mathematically as a Markov decision process, MDP. It's a framework well-suited for modeling sequential decision-making in situations where outcomes are partly random and partly under the control of a decision-maker. This is why RL is so powerful for problems involving sequential decision-making and delayed rewards, think game playing, AlphaGo, robotics control, and developing autonomous systems, where the agent learns by interacting with a dynamic, complex environment.
Let's do a deep dive into Q learning. This sounds like a foundational and widely used algorithm in reinforcement learning, one that often comes up in discussions about how AI learns to play complex games like Atari or even Go.
Q learning is definitely a cornerstone of modern RL. It's classified as a model-free and off-policy algorithm.
Okay, what do model-free and off-policy mean?
Model-free means the agent doesn't need to explicitly learn a model of the environment's dynamics. Like, it doesn't need to learn the exact probability of transitioning from state A to state B if it takes action X. It can learn the optimal policy directly from its interactions, from the rewards it gets.
Doesn't need to build a perfect simulation of the world.
Correct. And off-policy means it can learn the value of the optimal policy, the best way to act, even while it's following a different, often more exploratory policy during the learning phase. It learns about the best path while sometimes wandering off it.
Okay. So how does it learn? What's the Q in Q learning?
The core of Q learning is a function called the Q function, which is typically stored in a lookup table known as the Q table. This table holds a value for every possible state-action pair. This value, QSA, is the Q value.
The quality value.
Exactly. It represents the quality or expected long-term value of taking action A's in state S. More formally, it's the expected total future discounted reward the agent will receive if it starts in state S, takes action A, and then follows the optimal policy thereafter.
Discounted meaning future rewards are worth slightly less.
Yes, usually. It encourages acting sooner rather than later. Think of the Q table as a constantly updated cheat sheet the agent builds over time. For any situation state, it can look up the expected value of each possible action and choose the best one.
Okay, so how does it build this Q table?
The Q learning process is iterative, happening over many cycles of interaction. First, you initialize the Q table. You create a Q table with dimensions corresponding to the number of states and the number of actions. All Q values are typically initialized to 0 or small random numbers, starting from scratch.
Blank slate.
Next, you choose an action. From the current state S, the agent selects an action A. To manage that exploration-exploitation trade-off we discussed, this choice is often made using an epsilon-greedy strategy. With a small probability, epsilon, the agent chooses a completely random action exploration.
Case of jams.
Right. Otherwise, with probability 1 epsilon, it chooses the action with the highest current Q value for that state exploitation, leveraging what it has already learned.
Does what it thinks is best.
Then, the agent performs the action and observes the outcome. The agent takes the chosen action A, the environment responds by transitioning to a new state S, and importantly provides numerical reward R for that action.
Sees what happens.
Finally, and this is the core, the Q value is updated. The Q value for the state action pair that was just executed is updated using a specific formula derived from the Bellman equation. Conceptually, this update rule does the following. It nudges the current Q value towards a target value. This target is calculated based on the immediate reward R received, plus the estimated best possible future reward obtainable from the new state S, discounted by a factor gamma. There's also a learning rate, alpha, that controls how much we update the Q value based on this new information.
So it updates its estimate based on the actual reward and the potential future reward.
Precisely. It learns from the immediate consequence and its estimate of the long-term value from the next state. This continuous self-correction helps the agent learn from its experiences and refine its understanding of which actions are most valuable in different situations. The agent then sets the new state S's as the current state and repeats the entire process. Choose action, observe, update Q value.
And over time.
Over many, many iterations, the Q values in the table gradually converge towards their true optimal values, providing the agent with a reliable policy for maximizing its cumulative reward.
Fascinating. It sounds like the reward design is critical, though.
Absolutely critical. This brings up a fascinating and often challenging aspect of reinforcement learning, the design of the reward function itself. This is a form of high-level, goal-oriented programming. The human doesn't specify how to achieve a task, but rather what constitutes success by carefully defining the rewards.
You tell it what's good, not how to get it.
Exactly. For instance, a sparse reward function, like giving a +1 only for winning a game and O otherwise, can make learning very slow because most actions give no feedback. But it may lead to more robust general strategies. A dense reward function, small positive rewards for making good intermediate moves, like capturing a piece in chess, can speed up learning but risks what we call reward hacking.
Reward hacking?
Yeah, where the agent learns to cleverly maximize those intermediate rewards in a way that doesn't actually achieve the overall goal, like learning to wiggle back and forth to collect points in a game instead of finishing the level.
Huh. I can see that.
This makes the design of the reward function a critical and often challenging aspect of applied reinforcement learning, as it directly shapes the agent's learned behavior. For complex, real-world tasks like autonomous driving, defining a perfect reward function that covers all possible scenarios and edge cases is a major barrier to safe and widespread deployment. It highlights the subtle but crucial human input required even for these self-learning systems.
So we've talked about the paradigms of learning: supervised, unsupervised, reinforcement. Now let's talk about the powerful machinery that has enabled the most significant AI breakthroughs of the last decade: deep learning, or DL.
Right. This is where things get really powerful.
This is the sophisticated architecture that takes all those learning principles we've discussed and really puts them to high gear, transforming what AI can achieve, especially with complex data.
That's right. Deep learning is a specialized subset of machine learning, and its key difference lies in its architecture and its approach to data representation. A crucial distinction is in the process of feature engineering.
Okay, what's that?
In many traditional machine learning workflows, a human expert has to manually identify and extract relevant features from raw data to feed into the algorithm. For instance, to classify an image of a car, a human might need to define features like has wheels, has windows, is a certain shape, maybe has a metallic texture.
Telling the algorithm what to look for.
Exactly. This is a time-consuming process that requires significant domain expertise. Deep learning algorithms, in contrast, automate this process of feature extraction. Through their layered structure, they can learn a hierarchy of features directly from the raw data itself.
It learns the important features on its own.
It does. This ability is what makes deep learning exceptionally effective for processing complex, unstructured data like images, text, and audio, where manually defining all the relevant features would be nearly impossible for humans. Think about defining the features of human speech.
Yeah, impossible. And the models at the heart of deep learning are artificial neural networks, or ANNs. Loosely based on the brain.
Very loosely inspired, yes. An ANN is made up of simple processing units called nodes or neurons, which are organized into distinct layers.
Layers, okay.
A typical neural network has 3 types of layers. First, an input layer, which receives the initial raw data, for example, the individual pixels of an image or the numerical representation of words in a sentence. Second, one or more hidden layers, which are situated between the input and output layers. This is where the majority of the computation and that hierarchical feature learning actually occurs. They do the heavy lifting.
The thinking part, sort of?
Sort of. And third, an output layer, which produces the final result of the network, whether that's a classification label, cat or dog, or predicted value, like a stock price.
Input, hidden, output.
How does the learning happen within these layers?
The learning process within an ANN is driven by two key mechanisms.
Yeah.
Forward propagation and back propagation.
In forward propagation, when data is fed into the input layer, it travels forward through the network layer by layer. Each neuron in a hidden layer receives inputs from the neurons in the previous layer. It then calculates a weighted sum of these inputs, adds a value called a bias, and applies a nonlinear activation function to the sum to determine its own output. This output is then passed on as input to the next layer. This process continues all the way until the output layer produces a final prediction.
So the data flows through, getting transformed at each layer.
Exactly. Then comes back propagation. After a prediction is made, it's compared to the true value in the case of supervised learning to calculate an error. How far off was the prediction?
The error calculation again.
Right. This error is then propagated backward through the network, from the output layer all the way back towards the input layer. As the error travels backward, the algorithm calculates how much each neuron's connection weight and its bias contributed to the total error. It then adjusts these weights and biases slightly in a direction that will reduce that error for the next time it sees similar data.
Tweaking the connections to do better next time.
Precisely. This entire process of forward propagation, making a prediction, and back propagation, learning from the error, is repeated thousands or even millions of times with the training data, allowing the network to gradually learn the optimal weights and biases that minimize the error and produce accurate predictions. It's like fine-tuning a massively complex instrument.
So we hear about deep learning all the time. What does deep actually signify? What does adding more layers do for a neural network that makes it so remarkably powerful?
That's precisely it. The depth is key. Deep simply refers to the presence of multiple hidden layers, often more than two, and sometimes hundreds or even thousands in modern architectures. This depth is what gives deep learning its remarkable power.
How? What do the extra layers achieve?
Each layer in the network learns to recognize features at a different level of abstraction, effectively creating that hierarchical representation of the data we mentioned.
Okay, can you give an example?
Sure. Take image recognition again. The very first hidden layers might learn to detect very simple, low-level features, things like edges, corners, basic color gradients in the image pixels.
Lines and dots.
Pretty much. The intermediate layers might then combine these simple features to learn more complex patterns, like textures, fur, metal, or specific shapes such as an eye, a nose, or a wheel.
Building blocks.
Building blocks, exactly. Then, deeper layers would assemble these shapes and patterns to recognize parts of objects, for example, a whole face or a car's body. And finally, the deepest layers can combine these parts to recognize the entire object itself, whether that's identifying it as a person or a car or a specific breed of dog. This layered learning of increasingly complex features, from simple lines to complex objects, is what gives deep learning its impressive capabilities, especially with perception tasks.
That makes sense. The hierarchy is powerful.
It really is. This ability to learn features automatically and hierarchically has led to the development of several specialized deep learning architectures, each tailored to different types of data and tasks.
Like different tools for different jobs.
Exactly. Convolutional neural networks, CNNs, are the workhorses of computer vision. They use a special mathematical operation called convolution, which is great for processing grid-like data, such as the pixels in an image. They're exceptionally good at detecting spatial hierarchies of features, making them ideal for tasks like image classification, object detection, and facial recognition.
CNNs for images. Got it.
Then we have recurrent neural networks, RNNs, which are designed to handle sequential data like text or time series data like stock prices over time. They feature internal loops or memory cells that allow information to persist from one step in the sequence to the next, giving them a form of memory to understand context.
So they remember what came before in the sequence.
Exactly. A more advanced type, long short-term memory, LSTM networks, are a special kind of RNN particularly effective at capturing long-range dependencies in sequences, making them useful for machine translation and speech recognition where context from much earlier might be important.
Okay, RNNs and LSTMs for sequences.
And then, The true game changer in recent years has been transformers, introduced in a groundbreaking 2017 paper titled Attention is All You Need.
Great title.
Isn't it? The transformer architecture has truly revolutionized natural language processing, NLP. It fundamentally discards the sequential recurrent structure of RNNs and instead relies heavily on a mechanism called self-attention.
Self-attention.
Yes. This allows the model to weigh the importance of all other words in a sentence when processing a single word, regardless of their distance. This enables it to capture complex, long-range dependencies far more efficiently and effectively than previous architectures.
So it looks at the whole sentence at once, kind of?
In a sense, yes, it considers the relevance of all parts simultaneously. This particular architecture is now the foundation for most modern large language models, LLMs, including the widely known GPT series from OpenAI, Google's LaMDA, and PaLM, and others. They are incredibly powerful for text generation, translation, summarization, and more.
Transformers are behind the current LLM boom.
Largely, yes.
It's truly amazing how far the algorithms have come. But it's important to remember, you mentioned this earlier, that the incredible success of these complex deep learning architectures isn't just an algorithmic story. It's inextricably linked to massive advances in hardware, right?
Absolutely crucial. You can't separate them. The core mathematical operations in deep learning, like matrix multiplications, are highly parallelizable. You can do lots of calculations at the same time, while the theoretical concepts of neural networks have actually existed for decades.
Since McCulloch and Pitts in the 40s.
Exactly. Their practical application on a large scale was computationally prohibitive for a long time. So the modern deep learning boom was truly made possible by the widespread availability of graphics processing units, GPUs.
The gaming chips.
The gaming chips. They were originally developed for the parallel processing demands of rendering complex graphics in video games, but proved to be perfectly suited for the parallel computations needed to train neural networks. This deep codependency means that the future of AI is shaped not only by software and algorithmic innovation, but also by continuous advances in hardware engineering.
Lesser chips, better AI.
Pretty much. This includes the development of specialized AI chips like Google's TPUs, tensor processing units, and other NPUs, neural processing units, designed specifically for AI workloads. And alongside that, the critical need to manage the immense energy consumption of training and running these increasingly powerful models. That's becoming a major concern.
We've talked a lot about the theoretical foundations of AI and machine learning. Now let's bring it to life and see how these concepts were actually translated into tangible, real-world applications. Building and deploying an ML model isn't just flipping a switch, right? It's a whole process.
Not at all. It's a structured, iterative process known as the ML lifecycle. It really revolves around three primary artifacts: the data you use for training, the ML model itself, the algorithm with learned parameters, and the code that trains the model and integrates it into a final product or system.
Okay, the life cycle. What are the main phases?
That's right. The life cycle is a highly collaborative and cyclical process, often requiring teams to revisit earlier stages as they gain more insight or as things change. It typically starts with phase 1, problem definition and planning.
Start with the why.
Exactly. Before any data is collected or code is written, a project absolutely must begin with a clear and well-defined objective. This ensures the project aligns with actual business goals and is technically feasible. This involved defining the business problem, translating a broad challenge like reduce customer churn into a specific ML task, such as build a model to predict the probability of customer churning in the next month, which is a classification problem.
Making it concrete.
Making it concrete. You then establish success metrics, defining clear, measurable, key performance indicators, or KPIs. These should include both technical metrics for the model, like accuracy, precision, recall, and business metrics that matter to the organization, like reduction in churn rate, cost reduction, increased user engagement. How will we know if this works?
Measuring success.
And finally, you assess feasibility and resources. Is the data actually available? Is it good enough? Do we have the computational resources, like GPUs, needed? Does the team have the right expertise? This is a crucial reality check to determine if the project is viable and if you have what you need to actually solve it before you invest heavily.
Okay, plan first, then what? Data.
Then comes the data phase, yes. Phase 2, data engineering, collection, and preparation. This phase is often the most time-consuming and, critically, the most important part of the entire life cycle.
Garbage in, garbage out.
That's the classic saying, and it's absolutely true for ML. The quality of your final model is fundamentally dependent on the quality of the data used to train it. This phase involves several steps. First, data collection. Gathering relevant data from various sources, internal databases, APIs, user activity logs, maybe third-party data sets. Ensuring the collected data is diverse and representative of the problem domain is crucial to avoid building a model that underperforms on certain groups or scenarios later on.
Get the right stuff.
Then comes data cleaning, because raw data is almost always messy. It's full of errors, missing values, duplicates, inconsistencies, outliers, you name it. This step handles all of that, maybe imputing missing values, removing duplicates, correcting inconsistencies, deciding how to handle extreme outliers. It's often tedious, but vital.
Tidying up.
Tidying up. Next, exploratory data analysis, EDA. Here, data scientists use statistical analysis and visualization tools to really understand the data structure, identify patterns, uncover initial insights, check assumptions. This informs subsequent steps like feature engineering. You have to understand your data before you model it.
Get to know the data.
Then you move into data transformation and feature engineering. This is about converting the cleaned, raw data into a format suitable for machine learning algorithms. They often need numbers, not text, for instance. Key activities include scaling, where numerical features like age and income are normalized onto a common scale, preventing features with larger values from disproportionately influencing the model. Encoding converts categorical variables like color or city into a numerical format, often using techniques like one-hot encoding. And feature creation or feature engineering.
This sounds important.
It is. This involves engineering new, potentially more predictive features from existing raw data. For example, extracting day of the week or isoliday from a raw date column might be much more useful for a sales forecasting model. This often requires domain knowledge and creativity.
Making the data more useful for the model.
Exactly. For supervised learning, you then have data labeling, manually or semi-automatically annotating the data with the correct output labels. Spam, not spam. Cat dog. This can be a massive, expensive effort for many projects, requiring significant human input. Finally, the prepared dataset is split into 3 distinct subsets. The training set, typically 70–80% of the data, used to actually train the model parameters. The validation set, a smaller subset used during training to tune the model's hyperparameters and prevent overfitting. And the test set, a final holdout subset the model has never seen before, used for a final, unbiased evaluation of its performance after training is complete.
Train, validate, test. Keeps it honest.
Keeps it honest, exactly. Phase 3, model engineering, training, and evaluation. With the data prepped, you move into the core modeling work. This involves model selection, choosing appropriate algorithms like decision tree, logistic regression, neural network based on the problem type, the data characteristics, and the trade-offs, interpretability versus accuracy you identified in the planning phase.
Picking the right tool.
Then model training, feeding the prepared training data to the chosen algorithm. The algorithm iteratively adjusts its internal parameters, weights and biases, to minimize a predefined loss function, effectively learning the underlying patterns from the data. After training, model evaluation rigorously assesses the model's performance on that unseen test set using those success metrics defined earlier. The key question is, does the model generalize well to new data it hasn't been trained on?
Does it work in the real world?
Pretty much. Finally, hyperparameter tuning optimizes the model further by fine-tuning its hyperparameters, those configuration settings not learned from data but set by the engineer beforehand, like the learning rate in Q-learning or the number of trees in a random forest or the K and K-means. Techniques like grid search or random search are often used to systematically explore different combinations of hyperparameters to find the settings that yield the best performance on the validation set.
Fine-tuning the settings. And the final phase, phase 4. Model deployment and monitoring is all about moving that model from the developer's laptop or server into live production, getting it out to the people or systems that will actually use it.
Precisely. This is where the rubber meets the road, taking the validated model and integrating it into an existing software application or system so it can make predictions on live incoming data. There are several common deployment strategies.
Like?
Real-time or online. Inference means the model is deployed, often as an API endpoint, providing instant predictions on demand. This is essential for things like real-time fraud detection as a transaction happens, or interactive recommendation engines updating as you browse.
Immediate answers.
Batch inference processes large volumes of data in batches at scheduled intervals, maybe overnight. This is suitable for non-time sensitive tasks like generating daily sales forecasts or processing large logs.
Done periodically.
And edge deployment involves deploying the model directly onto a user's device, like a smartphone camera app doing object recognition, or an IoT sensor doing anomaly detection. This allows for low-latency predictions without needing to constantly communicate with a central server, which is crucial for privacy and speed in certain applications.
Running on the device itself.
Right. Once deployed, the job isn't done. Monitoring and maintenance are critical. A deployed model isn't static. Its performance must be continuously monitored in the real world. Over time, a model's accuracy can degrade.
Why would it degrade?
Due to phenomena known as model drift or data drift. This occurs when the statistical properties of the live data the model is seeing in production start to change and no longer match the data the model was originally trained on. The world changes, user behavior changes, and the model gets out of sync.
The model gets stale.
Exactly. When monitoring reveals a significant drop in performance, the model must be retrained on fresh, relevant data to adapt to the new reality. This can be a manual process triggered by an alert, or in mature systems, it can be automated through a continuous integration, continuous deployment, or CI/CD pipeline for ML that regularly retrains and redeploys the model without manual intervention.
Keeping it fresh automatically. This entire complex end-to-end life cycle, especially the challenges of deployment, monitoring, and ongoing maintenance, sounds like it needs more than just data scientists.
Absolutely. It has given rise to a whole new discipline, MLOps, or machine learning operations.
MLOps. Heard that term?
MLOps is essentially applying the principles of DevOps, things like automation, collaboration, version control, continuous integration, and delivery directly to the machine learning lifecycle. The emergence of the MLOps engineer as a distinct role really underscores that a successful AI project is a highly collaborative team effort. It requires expertise not just in data science and algorithm development, but also in software engineering, infrastructure management, cloud platforms, and operations.
Bridging the gap between research and production.
Precisely. What's often surprising to companies just starting with AI is that the primary bottleneck in successful AI adoption isn't usually the lack of powerful algorithms anymore. It's often the lack of mature MLOps practices to reliably and efficiently bridge that gap between the research lab model and a robust, scalable, monitored real-world application. Getting a model to work once is one thing. Getting it to work reliably and continuously at scale is a whole different ballgame.
So what does all this theory mean for you, the listener? Let's look at one of the most pervasive AI applications you probably interact with every single day. Recommendation engines. Think about it. Netflix suggesting your next binge watch, Amazon showing you products you might like, Spotify curating a personalized playlist. They are absolutely everywhere, shaping our choices constantly.
They certainly are. They've become fundamental to the user experience online. At their core, a recommendation engine or recommender system is an information filtering system that leverages AI, primarily machine learning, to predict a user's preference or rating for an item, like a movie, product, or song, and then suggests relevant items they might like.
Helping us find stuff in massive catalogs.
Exactly. These systems are absolutely critical for businesses in the digital space because they significantly enhance user experience, drive engagement, keeping you on the platform longer, and ultimately boost sales by helping users navigate incredibly vast catalogs of content or products that would be impossible to browse manually.
How do they know what I like? What data do they use?
The engine's operation relies on analyzing massive amounts of user data, which can be broadly categorized into two types: explicit data and implicit data. Explicit data is information that users directly and consciously provide, such as movie ratings, giving a film 4 out of 5 stars, writing product reviews, or clicking like on an article.
Stuff I tell it directly.
Right. Implicit data, on the other hand, is information inferred from a user's behavior, things they do without explicitly stating a preference. This includes their browsing history, which items they click on, their search queries, their purchase history, even how long they watch a video or listen to a song.
My digital breadcrumbs.
Your digital breadcrumbs, exactly. This rich blend of explicit and implicit data feeds the system, allowing it to build a surprisingly nuanced digital intuition about your preferences and habits over time.
And at the heart of these recommendation engines are the filtering algorithms that process all this data to generate suggestions. I understand there are two fundamental approaches: content-based filtering and collaborative filtering.
That's right. Those are the two main pillars, although modern systems often blend them. Let's start with content-based filtering.
Okay.
Content-based filtering recommends items based on their intrinsic attributes and a user's historical preferences for those attributes. The core principle is straightforward. If you like this item, you will also like other items that are similar to it based on its content.
Like recommending sci-fi movies if I watch a lot of sci-fi.
Exactly. How it works is that the system first creates a profile for each user based on the features of items they have previously interacted with positively, liked, rated highly, purchased. For instance, if you like a movie, its features might be its genre, sci-fi, comedy, director, actors, plot keywords. For a product, it could be its category, brand, color, price range.
Building my taste profile.
Right. The system then analyzes the features of other items in the catalog and recommends those that have a high similarity score to the user's profile. This is essentially a supervised learning problem underneath learning to predict a user's preference for an item based on its content features matching their profile.
What are the pros and cons of this approach?
The advantages of content-based filtering are that it's very effective at recommending niche items. If you like Hungarian folk music from the 1970s, it can find more of that, assuming the metadata is good. And it doesn't require data from other users to make a recommendation for a specific user. This helps to address the cold start problem for new items. As soon as a new movie is added with its genre and actors tagged, it can be recommended to users who like similar content.
Okay, good for niche tastes
Sure.
and new items. Downsides.
Its main disadvantage is its tendency to create a filter bubble, or echo chamber. It can only recommend items that are explicitly similar to what a user has already liked, making it difficult for the user to discover new and diverse interests outside their established patterns. You get stuck in a rut.
They're the same.
More of the same. The quality of recommendations is also heavily dependent on the quality and completeness of the item's metadata. If the movie isn't correctly tagged with its genre or actors, the system won't know to recommend similar ones. It needs good descriptions.
Got it. So what about the other main type, collaborative filtering?
Now, collaborative filtering is the most widely used and often considered more powerful approach because it's fundamentally different. It operates on a principle often summarized as users who agreed in the past will agree in the future, or people like you also liked this.
It uses other people's behavior.
Exactly. Instead of looking primarily at individual item features, it analyzes the collective behavior of all users. How it works is by analyzing a large matrix of user-item interactions. Imagine a huge spreadsheet where rows represent users, columns represent movies, and the cells contain their ratings, or maybe just a 1 if they watched at 0 if not.
The big matrix of everybody's tastes.
Right. It then identifies users who have similar tastes or similar patterns of interaction, that is, users who have rated the same movies similarly in the past. Once these similar users or neighboring users are found, the system recommends items that those similar users have liked, but that the current user have not yet seen or interacted with.
Finding my taste twins.
Finding your taste twins. This technique allows for what we call serendipitous recommendations, suggesting items that a user might love but would never have discovered on their own because they are not obviously similar in content to their past choices. It's how Netflix might recommend a quirky indie film or a foreign documentary you never knew you'd like, simply because other people with similar overall viewing habits enjoyed it. It breaks the filter bubble.
That sounds powerful. Are there different ways to do collaborative filtering?
Yes, there are two main types. User-based collaborative filtering directly finds users who are similar to the target user and then recommends items that those similar users liked. Item-based collaborative filtering, which became popular at places like Amazon, finds items that are similar to each other based on how all users have rated them in aggregate. The logic here is more like, users who like this item also tended to like that item. It recommends items similar to those the user already liked, but the similarity is based on collective behavior, not content.
Okay. What are the advantages and disadvantages here?
The key strength of collaborative filtering is its ability to generate novel and diverse recommendations that go beyond a user's established tastes, enabling that serendipity. It often leads to higher user satisfaction because it feels like the system gets you on a deeper level. However, it also suffers from a significant cold start problem, but for new users this time.
Because a new user has no history.
Exactly. If a new user joins the platform and has no interaction history, no ratings, no purchases, the system cannot find similar users and therefore cannot make meaningful collaborative recommendations initially. It also struggles with data sparsity. That huge user item matrix is typically mostly empty because most users have only rated or interacted with a tiny fraction of the millions of available items. This makes it mathematically harder to find users with significant overlap in their tastes.
So, with these different strengths and weaknesses for content-based and collaborative, how do the big players like Netflix or Spotify actually handle it? You mentioned serendipitous recommendations. How do they ensure that blend of familiar and surprising? Do they just pick one?
That's a great question, and the answer is usually no. They don't just pick one. It's where the magic, or rather the sophisticated engineering, really happens. Most modern recommendation systems, including Netflix's, actually use hybrid models.
Mixing them together.
Exactly. These systems combine collaborative filtering, content-based filtering, and sometimes other techniques like demographic filtering, recommending based on age location, though this is often less powerful and can be problematic, to overcome the limitations of each individual approach and produce more robust, accurate, and satisfying recommendations overall.
So how might that work in practice?
For example, a hybrid system might initially use content-based filtering to handle new items or new users, effectively mitigating that cold start problem we discussed. As soon as a new movie has metadata, it can be recommended based on content. As soon as a new user likes one movie, content-based can suggest similar ones. Then, as more user interaction data becomes available for that user, the system can transition to relying more heavily on the more powerful collaborative filtering signals to provide those diverse and serendipitous suggestions. They often use complex models that learn how to optimally weight the signals from both approaches.
Using the best of both worlds.
Using the best of both worlds. What's truly fascinating here, though, and often underestimated by users, is that these algorithms aren't just passive predictors reflecting your existing taste. While their explicit goal is to predict what you'll like, their operational reality is far more complex and interactive.
Also,
By consistently exposing a user to certain types of content based on past behavior, the system creates a powerful feedback loop. A user who watches a science fiction movie is recommended more science fiction, which they might then watch, further strengthening their profile's association with that genre and making future sci-fi recommendations even more likely.
so it reinforces itself.
It reinforces itself. In this way, the algorithm is not merely a passive predictor, but an active participant in shaping and reinforcing a user's tastes and consumption habits over time. This has profound implications for culture and commerce. These engines can amplify trends rapidly, create rich get richer effects where popular items become even more dominant and harder to displace, and potentially, some argue, lead to a homogenization of tastes on a global scale if everyone is steered towards similar mainstream content. It's a complex dance between predicting what you like and subtly nudging you towards what it thinks you should like based on the data.
Now let's shift to another AI application you probably use daily. Virtual assistants. Siri, Alexa, Google Assistant. These systems allow you to use your most natural form of communication language to interact with technology. They seem like prime examples of natural language processing, or NLP, in action.
Absolutely. They are arguably the most visible and widely adopted application of NLP today. Natural language processing, NLP, is a specialized subfield of AI that focuses on enabling computers to understand, interpret, manipulate, and generate human language in both its written text and spoken speech forms.
Understanding and producing language.
Right. It's an incredibly interdisciplinary field, drawing on computer science, linguistics, artificial intelligence, and machine learning. The ultimate goal of NLP is to create seamless, intuitive communication between humans and machines, something that has historically been an enormous challenge due to the inherent ambiguity, context dependence, and sheer complexity of human language. It's easy for us, hard for computers.
The seemingly simple act of asking a virtual assistant a question, "What's the weather like?" and receiving a coherent answer actually involves a complex, multi-stage pipeline of specialized AI models working in concert behind the scenes. It's pretty fascinating to peel back the layers on that.
It truly is. It looks simple, but there's a lot going on. Step 1. Automatic speech recognition, ASR. The process begins when a user speaks a command, usually preceded by a wake word like, "Hey Siri," or "Okay Google," that activates the listening mode.
The wake word.
The device's microphone captures the audio, and an automatic speech recognition, or ASR, model takes over. The ASR system's sole job is to convert those analog sound waves of human speech into digital text, transcribing what you said.
Which sounds hard enough on its own.
Oh, it's incredibly challenging. Think about the immense variability in human speech, different accents, dialects, pitches, tones, speaking speeds, plus the omnipresent challenge of background noise, echoes, maybe mumbling.
Right, understanding me when I've just woken up.
Exactly. Trying to understand someone with a heavy accent in a crowded, noisy room, that's the kind of problem ASR is constantly tackling. Modern ASR systems overcome this using sophisticated deep learning models, often CNNs and RNNs transformers, trained on thousands upon thousands of hours of diverse speech data to achieve high accuracy, translating the messy audio input into clean text output.
Okay, so sound waves become text. What's next?
Step 2, natural language understanding, NLU. Once the user's speech has been transcribed into text, the next crucial step is to figure out what that text actually means. This is the domain of natural language understanding, or NLU, a core component of NLP. The NLU model analyzes the grammatical structure, the vocabulary, and the semantics of the text to determine the user's intent and to extract key pieces of information known as entities.
Intent and entities. Can you give an example?
Sure. If you say, schedule a meeting with Jane for tomorrow at 2 p.m., the NLU model would parse this sentence. The intent might be identified as schedule meeting, and the entities extracted would be something like contact name, Jane, date, tomorrow, and time, 2 p.m. It pulls out the key variables needed to fulfill the request.
Breaking down the sentence into meaningful parts.
Exactly. To achieve this, the NLU system performs several underlying NLP tasks. These can include part of speech, POS, tagging, identifying nouns, verbs, adjectives, named entity recognition, NER, identifying people, places, dates, times, like in the example, and maybe word sense disambiguation, figuring out which meaning of book you intend in book a flight versus read a book.
Okay, so now the assistant understands what I want. Then
Step 3. Action execution and natural language generation, NLG. After the intent and entities have been successfully extracted, the virtual assistant's internal logic or dialogue manager determines the appropriate action to take. This often involves interacting with other applications or services via APIs, for instance, accessing your calendar app to check for availability and add the meeting, or querying a weather service API.
talking to other apps.
Right. Once that action is completed, or if the request was just a question needing an answer, the final step is to communicate back to the user in a natural way. This is handled by a natural language generation NLG model. The NLG system takes the structured output from the action phase, for example, a confirmation code like meeting scheduled or raw weather data, and formulates a coherent, grammatically correct, human-like sentence, such as, okay, I've scheduled a meeting with Jane for tomorrow at 2 p.m., or the weather tomorrow will be sunny with a high of 25 degrees.
Turning the computer's result back into language.
Exactly. This generated text is then fed into a text-to-speech, TTS engine, the counterpart to ASR, which synthesizes the audio output that you hear as the assistant's voice.
So it's pretty clear that machine learning, and especially deep learning, play a huge role throughout this pipeline. Modern NLP systems have moved far beyond the rigid, rule-based approaches that defined earlier attempts at language understanding, right?
Absolutely. Those old systems were brittle and couldn't handle the variation of real language. Today's virtual assistants are powered by highly sophisticated deep learning models, particularly architectures like LSTMs and, as we mentioned, the more recent and powerful transformers. These models are trained on massive data sets of text and speech scraped from the internet and licensed sources, allowing them to learn the complex patterns, context, and incredible nuances of human language far more effectively than was previously possible.
They learn the rules from data, not from programmers writing grammar rules.
Precisely. This data-driven learning is what enables them to handle the ambiguity inherent in language. Did you mean two, or two? And to continuously improve their performance over time as they process more and more interactions and get retrained on new data.
So if we connect this to the bigger picture, the perceived intelligence of a virtual assistant, the feeling that it understands you, it isn't really one single general AI brain thinking in there, is it?
Not at all. That's a key takeaway. It's an emergent property. It arises from a highly sophisticated and hopefully seamlessly integrated pipeline of multiple specialized narrow AI models, the ASR model, the NLU model, the dialogue manager, the NLG model, the TTS model, all working in concert, often interacting with external software applications and knowledge bases via APIs.
A team of specialists.
A team of AI specialists, exactly. Understanding this really demystifies the technology. It's not magic, but rather a remarkable feat of systems integration and applied machine learning engineering. This also implies that the future advancement of virtual assistants will depend not only on continued improvements in the core AI models themselves, better NLU, more natural NLG, but also critically on the development of standardized APIs and more robust integration capabilities. That's what will allow them to interact with an ever-expanding ecosystem of digital services and actually do more complex tasks for us beyond just setting timers and telling jokes.
Let's turn our attention now to computer vision. That's the field of AI focused on teaching machines to interpret and understand information from the visual world. Using digital images from cameras, videos, and those powerful deep learning models we just talked about, machines can now accurately identify and classify objects and then actually react to what they see.
Right. It's about giving machines the sense of sight in a functional way.
And facial recognition seems like one of the most prominent and, frankly, sometimes controversial applications of computer vision. It really shows how AI can perform complex visual pattern recognition tasks that were once exclusively the domain of humans.
It's definitely a flagship application, yes. The overarching goal of computer vision, more broadly, is to enable machines to derive meaningful information from visual inputs, images, videos, and then take actions or make recommendations based on that information. It seeks to replicate, or at least mimic, aspects of human vision, a process that involves not just seeing, but also understanding, interpreting, and contextualizing visual data. It's about teaching a computer to see in a way that's useful for a given task. Hashtag the facial recognition process.
So how does facial recognition actually work? If I use my face to unlock my phone, what's happening under the hood?
The process of identifying or verifying a person from a digital image or video frame involves a sequence of distinct steps, each typically powered by sophisticated deep learning algorithms these days.
Face detection. The first and most fundamental step is to simply locate all human faces within a given image or video stream. The system scans the input and identifies regions that correspond to a face, typically by drawing a bounding box around it to isolate it from the background noise.
Just finding the face, not knowing whose it is yet.
Exactly. The step answers the basic question. Is there a face in this image, and where is it located? This is distinct from actually recognizing who the face belongs to. It's a prerequisite.
Okay, found a face. Step 2.
Step 2, face analysis and feature extraction. Once a face is detected and isolated, the system meticulously analyzes its geometry. It identifies and measures key facial landmarks, points like the corners of the eyes, the tick of the nose, the corners of the mouth, the shape of the jawline.
Measuring the face's unique points.
Right. It measures the distances and relative positions of these landmarks. This detailed analysis is used to create a unique numerical representation of the face, often called a face print, or more technically, an embedding.
An embedding, like a fingerprint for the face, but numbers.
Exactly. Crucially, this face print is not a picture. It's a mathematical vector, a long string of numbers that uniquely encodes the spatial relationships and potentially the textures of the person's face. This conversion of complex visual data into a simplified, storable, and comparable numerical format is the absolute key to the entire process. It makes the visual information computable.
Turning a face into a math problem?
Essentially, yes. Step 3, face matching and identification. The final step is to compare that newly generated face print from the live camera feed, say, against a database of known face prints, like the one stored securely on your phone when you set up Face Unlock. The system calculates the mathematical similarity or distance between the new face print and those in the database.
Sees how close the numbers are.
Right. If a match is found in the database that exceeds a predefined confidence threshold, meaning the numerical vectors are sufficiently similar, the system can then make an identification.
Right.
This person is Jane Doe from our employee database. Or a verification. Yes, this person is the authorized owner of this phone.
Unlock the phone if the match is good enough.
Precisely. Hashtag the role of deep learning in CNNs. Now, it's important to stress that modern facial recognition technology, especially the high-accuracy systems we see today, is almost entirely driven by deep learning, and specifically by that class of neural networks we discussed, convolutional neural networks, CNNs.
CNNs again, perfect for images.
Exactly. CNNs have truly revolutionized computer vision because their architecture, with its convolutional layers and pooling layers, is exceptionally well-suited for processing grid-like data, such as the pixels in an image. They are designed to automatically learn and detect relevant spatial hierarchies of features in visual data.
And the power of CNN really comes from that hierarchical, multi-layered structure, right?
Right.
Learning simple things first, then combining them, like how our own visual system might work.
That's the analogy, yes, though it's a simplification. The initial layers of the network learn to detect very simple low-level features, maybe edges at different orientations, corners, basic color gradients within the image pixels.
Lines and textures.
All right. Then, the intermediate layers in the network combine these simple features to learn more complex patterns and shapes, like the unique curve of a chin, structure of an eye or a nose, maybe the shape of an ear.
Facial parts.
Facial parts, exactly. And finally, the deepest layers assemble these components, these learned parts, to recognize the entire configuration of a face, learning representations that are robust to variations.
So it learns to recognize a face despite different angles or lighting.
To a remarkable degree, yes. To achieve this capability, these CNNs are trained on enormous datasets, often containing millions, sometimes billions, of diverse face images from a wide range of individuals, poses, lighting conditions, expressions, and occlusions, like wearing glasses or a hat. This extensive training allows the network to learn which facial features are most discriminative, that is, most effective for distinguishing one individual from another, while also learning to be robust or invariant to those common variations. That's why you can still unlock your phone with facial recognition even if you've changed your hairstyle slightly or aren't smiling. The learned embedding is designed to be stable.
But this incredible power also brings a critical challenge we hear a lot about: algorithmic bias. Sometimes these systems demonstrate lower accuracy for certain demographic groups, particularly women and people with darker skin tones. Why does that happen?
That's a crucial and well-documented issue. It's often a direct result of the training data itself being non-representative or imbalanced. If the massive data sets used to train these models predominantly feature faces from one demographic group, historically often lighter-skinned males, the algorithm simply doesn't get enough examples or variation to learn the distinguishing features for underrepresented groups as effectively.
So it's better at recognizing the faces it saw most during training.
Exactly. The model becomes optimized for the majority group in the data. This isn't necessarily intentional bias programmed in, but rather a bias learned from the data distribution.
Which leads to real-world harms and fairness issues.
Absolutely. This raises an important point. For a technology like facial recognition, which is intended for global application and often used in sensitive contexts like law enforcement or access control, data diversity isn't merely a theoretical nice-to-have for ethical reasons. It's a core component of functional accuracy and reliability. An algorithm that cannot reliably identify individuals from a specific demographic group is, by definition, a less accurate and less robust algorithm overall.
It just doesn't work as well for everyone.
Right. Consequently, efforts to improve these systems by carefully curating more inclusive and representative training datasets, actively seeking out and including diverse faces across gender, ethnicity, age, etc., are absolutely fundamental to improving the core performance and reliability of the technology itself. This necessity, however, often pushes technology companies into the complex and sometimes politically charged domain of demographic data collection and careful ethical curation, highlighting how real-world performance and fairness depend on much more than just the algorithms themselves. The data foundation is critical. ###4V. The broader context, ###A. The societal and economic dimensions of AI.
Beyond the fascinating tech and algorithms, it's clear AI is not just a technological shift. It's actively reshaping economies, challenging our ethical frameworks, and raising fundamental questions about the future of work, privacy, and even human agency. This is where the rubber really meets the road for all of us, isn't it?
You're absolutely right. The integration of AI into critical societal functions, from how we get news and recommendations to how loans are approved, to how medical diagnoses are assisted, and even potentially into areas like criminal justice or autonomous vehicles, has brought a host of complex challenges and ethical dilemmas right to the forefront.
Let's talk about algorithmic bias again. We touched on it with facial recognition, but it's broader than that, right?
Much broader. A fundamental challenge is that AI systems learn from data. And if that data reflects existing societal biases, historical discrimination, underrepresentation, systemic inequalities, then the AI model is likely to learn, perpetuate, and sometimes even amplify those biases.
It learns the biases in the data.
Exactly. An algorithm optimized purely for statistical accuracy on biased data will inevitably produce biased outcomes, even if there's no malicious intent from the developers. It simply learns the patterns it's shown, biases and all.
Can you give some examples?
Sure. In hiring and employment, AI tools are increasingly used to screen resumes or even analyze video interviews. If these tools are trained on historical hiring data where, for example, men were predominantly hired for certain roles, the AI might inadvertently learn to associate male-typical language or background with success, potentially penalizing qualified female applicants. Amazon famously scrapped an AI recruiting tool because it learned to penalize resumes containing the word women's and favored graduates of certain all-male colleges.
Wow.
Similarly, in criminal justice, there's concern about predictive policing algorithms or risk assessment tools used for sentencing or parole decisions. If these tools are trained on historical arrest data that itself reflects biased policing practices targeting minority communities, the AI might learn to predict higher risk for individuals from those communities, potentially leading to unfair cycles of surveillance and incarceration. It's a serious feedback loop concern.
So the AI inherits the problems from the past data.
It can, if not carefully designed and audited. Another critical concern is data privacy in the age of AI. AI systems are fundamentally data hungry, as we've said. They often require vast quantities of information, often personal information, to be trained effectively. This insatiable appetite for data creates significant privacy risks.
How so?
Well, first, the sheer scale of massive data collection raises concerns about how personal data is being used, stored, secured, and potentially shared, sometimes without the individual's full informed consent or understanding. There's also the risk of data repurposing data collected for one seemingly innocuous purpose, like improving a map service, might later be used for a completely different, unforeseen, and potentially more intrusive purpose, like targeted advertising or surveillance.
Using data in ways I didn't agree to.
Potentially, yes. And related to that is enhanced surveillance. Technologies like facial recognition in public spaces, combined with location tracking from our phones and monitoring of our online behavior, enable levels of surveillance that were previously unimaginable. This raises profound questions about personal freedom, anonymity, and the potential for misuse by governments or corporations.
The trade-off between convenience and privacy.
It's a constant tension. And then there's a fascinating technical challenge related to privacy regulations like GDPR's right to be forgotten, which grants individuals the right to have their personal data erased. This poses a significant technical hurdle for AI. Once personal data has been used to train a large, complex model, like a deep neural network, it becomes deeply embedded and distributed within the model's billions of parameters, those weights and biases. It's not like deleting a row in a simple database. Making the model completely forget that individuals' data influence is nearly impossible without retraining the entire model from scratch, which can be immensely costly and time-consuming.
So forgetting is hard for AI. This leads us directly to the quest for explainable AI, or XAI. As you've heard us mention, many of the most powerful AI models, especially those deep neural networks, operate as black boxes. While they can deliver remarkably accurate predictions, their internal decision-making processes are so incredibly complex that they're often opaque even to their own developers. It can be incredibly difficult, sometimes impossible, to determine precisely why a model made a particular decision, beyond simply stating it was based on the patterns in the training data.
And this lack of transparency isn't just an academic curiosity. It can be a fundamental barrier to trust and practical adoption in high-stakes domains. If a doctor cannot understand why an AI system recommended a specific treatment, they're unlikely to trust it with a patient's life. If a loan applicant cannot be told in clear terms why their application was denied, it undermines fairness and accountability. You can't appeal a decision you don't understand.
Right, you need to know the reasoning.
Exactly. In response to this challenge, the field of explainable AI, XAI, has emerged. XAI encompasses a growing set of methods and techniques specifically aimed at making the decisions and predictions of AI models transparent, interpretable, and understandable to humans, trying to peek inside the black box or build models that are inherently more transparent.
Why is XAI so important?
Its importance cannot be overstated for several reasons. It is crucial for building trust, as end users and stakeholders are more likely to adopt and rely on AI systems if they understand, at some level, the reasoning behind their outputs. It's also vital for ensuring fairness by allowing developers and auditors to probe models and check for hidden biases or discriminatory patterns. Furthermore, explainability is essential for improving and debugging models. By understanding why a model is making mistakes, developers can more effectively diagnose issues and enhance its performance and robustness. And finally, increasingly, it's needed for meeting regulatory requirements in sectors like finance and healthcare, where explanations for automated decisions may become legally mandated.
Okay, let's shift to another huge topic: the future of work and the economy. This is probably one of the most debated aspects of AI's impact.
It really is. With widely varying predictions, AI's economic impact has the potential for both unprecedented growth and significant disruption. When we talk about job displacement and creation, AI-driven automation is poised to transform the labor market, perhaps more profoundly than previous technological waves.
How so?
Many tasks, especially those that are routine, repetitive, predictable, and analytical, are highly susceptible to automation by AI. This is expected to lead to significant job displacement in roles such as data entry clerks, certain types of customer service representatives, truck drivers with autonomous vehicles, maybe even paralegals or basic accounting roles. While historical technological shifts have also displaced jobs, think weavers or elevator operators, AI is arguably unique in its potential ability to affect not just manual labor, but also certain aspects of white-collar, knowledge-based work that were previously considered safe.
So it's coming for office jobs, too.
Potentially aspects of them, yes. At the same time, AI is expected to create entirely new jobs that do not yet exist, particularly those requiring skills in managing, developing, auditing, maintaining, and working collaboratively alongside AI systems. Think AI trainers, ethicists, prompt engineers, MLO specialists, roles we couldn't conceive of a decade ago. The net effect on overall employment, whether AI will ultimately lead to mass unemployment or a net increase in jobs after a transition period, remains a subject of intense debate among economists and technology experts. There's no consensus.
A big unknown. What about economic growth and inequality?
Looking at economic growth and inequality, AI certainly has the potential to be a major driver of productivity and economic growth, with some estimates predicting it will add trillions of dollars to the global economy in the coming decades. However, there's a significant risk that these economic gains will not be distributed evenly across society.
The rich get richer.
That's the concern. AI could exacerbate income and wealth inequality by significantly increasing the value and wages of high-skilled workers who can effectively develop, manage, and leverage AI tools, like software engineers, data scientists, managers using AI insights, while simultaneously depressing the wages of low-skilled workers whose tasks are more easily automated, or forcing them into lower-paying service jobs. This could lead to a further polarization of the labor market, high-paying creative technical jobs, and low-paying service jobs, with the middle hollowing out and deepen societal divides. This is a crucial challenge for policymakers to address through education, retraining, and potential redistribution mechanisms.
It sounds like there are a lot of potential downsides or challenges. Is there a positive vision, too? What about AI for social good?
Absolutely, and this is incredibly important. There's a powerful and growing movement focused on purposely applying AI technologies to address some of the world's most pressing humanitarian and environmental challenges, often in alignment with frameworks like the United Nations Sustainable Development Goals, SDGs. AI, ultimately, as we said, is an amplifier. Its impact, positive or negative, depends heavily on the problems we choose to solve with it and how we choose to implement it. The AI for Social Good movement seeks to consciously direct this powerful tool toward positive outcomes for humanity and the planet.
What are some examples?
There are many promising application areas. In healthcare, AI models can analyze medical images, like X-rays or MRIs, to help diagnose diseases like cancer or diabetic retinopathy earlier and potentially more accurately than human experts in some cases. AI can also predict patient outcomes based on electronic health records, help discover new drug candidates, and even assist in developing personalized treatment plans based on an individual's genetics or lifestyle. There's huge potential to improve healthcare access and quality, especially in underserved regions globally, through remote diagnosis or AI-powered health assistance.
That sounds amazing. What else?
In climate change and environmental protection, AI can analyze vast amounts of satellite imagery and sensor data to monitor deforestation in near real time, track endangered species populations, predict the path and intensity of natural disasters like wildfires and hurricanes to aid response efforts, and optimize energy grids to integrate renewable sources more efficiently and reduce carbon emissions.
Using AI to understand and protect the planet.
Exactly. And in education, AI-powered adaptive learning platforms can provide personalized education tailored to the individual pace and learning style of each student. Imagine a tutor that adapts constantly to your needs. This holds immense promise for improving educational outcomes and bridging learning gaps, especially for students in remote areas or under-resourced schools who lack access to personalized human tutoring.
So huge potential for good. But are there challenges in using AI for social good, too?
Definitely. Despite its immense potential, the AI for social good sector faces significant challenges. Often there's a lack of access to high-quality, relevant, and unbiased data in these specific domains, like tracking poverty or rare diseases, compared to the vast data available for commercial applications like advertising. There's also often a disparity in funding and resources compared to commercial AI ventures. And critically, there's the need to ensure that solutions are designed thoughtfully and inclusively, involving the communities they aim to serve, to avoid inadvertently causing harm or perpetuating existing inequalities. The impact of AI on equity and well-being will ultimately be determined by our collective policy choices and priorities. whether we primarily foster commercial applications that may widen divides, or whether we deliberately create the incentives, funding structures, and ethical frameworks needed to steer this technology toward broadly beneficial outcomes for all.
So, what does this all mean as we wrap up? We've taken a deep dive into artificial intelligence, and it's clear it has transitioned from a somewhat niche academic concept to a practical, powerful reality that's fundamentally altering our technological and societal landscape.
It's truly transformative.
To recap the key points, the core of modern AI is its ability to learn from data. This is a true paradigm shift from traditional programming, enabling machines to perform tasks requiring intelligence, such as pattern recognition, prediction, and complex decision-making. The history of AI, as we discussed, isn't a simple linear march, but a series of cycles of breakthrough, hype, and sometimes disappointment or winter.
Followed by another spring.
Exactly. And the current boom, this AI spring or summer we're in, is fueled by an unprecedented convergence of three key enablers. Truly vast amounts of data, incredibly powerful computational hardware like GPUs, and revolutionary advanced algorithms, especially in deep learning.
And just to reiterate that taxonomy, the AI we interact with today is overwhelmingly artificial narrow intelligence, ANI. It excels at specific tasks, but crucially lacks the generalized, flexible intelligence of humans. The pursuit of artificial general intelligence, AGI, human-level AI, remains a long-term, ambitious, and as yet unrealized goal, despite what some headlines might imply.
Good distinction to keep making.
And the primary engine driving all this progress is machine learning, which operates through its three core paradigms: supervised learning, learning from labeled examples; unsupervised learning, finding patterns in unlabeled data; and reinforcement learning, learning through trial and error interaction. These paradigms are implemented through a diverse and growing toolkit of algorithms, with deep learning and its multi-layered artificial neural networks representing the state-of-the-art for solving many complex problems, especially those involving unstructured data like images, language, and audio.
So, thinking about the future. The path toward responsible and beneficial AI is a critical discussion we need to keep having. The future is not predetermined, is it? And expert opinions on AI's long-term impact seem deeply divided.
Very much so. You hear everything from utopian visions of AI curing diseases, solving climate change, and ushering in an age of abundance, to deeply dystopian concerns about mass unemployment, autonomous weapons, uncontrollable superintelligence, and the erosion of human autonomy.
A huge range of possibilities.
Huge range. But it's crucial to remember that the technology itself is fundamentally a tool. A very powerful tool, yes, but still a tool. Its ultimate effect on humanity will be determined not by the technology itself, but by the choices we make collectively and individually in its development, deployment, and governance.
It's up to us how we use it.
Exactly. Navigating this complex future requires a concerted multi-stakeholder effort involving technologists, researchers, policymakers, businesses, educators, ethicists, and the public at large. The path toward a truly responsible and beneficial AI ecosystem, I believe, must be built on several key pillars or ongoing efforts.
What would those be?
First, continually addressing bias and promoting fairness. This means diligently working to ensure training data sets are comprehensive, representative, and audited for biases, and developing algorithms and evaluation metrics that explicitly prioritize fairness alongside accuracy. As we discussed, functional accuracy often depends on this.
Right. Fairness is part of performance.
Second, protecting privacy.
Yeah.
This requires establishing strong data governance frameworks, enforcing principles of data minimization, collecting only what's necessary, ensuring meaningful user consent, enhancing data security, and exploring privacy-preserving techniques like federated learning or differential privacy.
Handling data responsibly.
Third, demanding transparency and explainability. As AI models become more complex and are deployed in high-stakes environments, that black box problem becomes increasingly unacceptable. Pushing for the development and adoption of explainable AI, XAI, is absolutely critical for accountability, for debugging these systems, for building public trust, and for ensuring meaningful human oversight. We need to understand why.
Opening the black box.
Or at least making it translucent. And finally, it's about proactively managing economic and social transition. We can't ignore the potential disruption. This requires investing significantly in education and retraining programs to help workers adapt to changing skill demands, strengthening social safety nets to support those displaced by automation, and exploring new models of work, potentially like universal basic income or adjusted work weeks, to ensure that the immense benefits of AI-driven productivity are shared broadly and contribute to overall societal well-being rather than just concentrating wealth.
So what does this all mean for you, the listener, and for all of us? The trajectory of AI is not some kind of technological inevitability unfolding before us. It is fundamentally a reflection of our human priorities, our values, our choices. The central challenge, maybe the central challenge of the coming decades, will be to guide its development with wisdom, foresight, and a steadfast commitment to the human values like fairness, autonomy, dignity, well-being that we wish to preserve and promote. The future ultimately will be shaped not just by what AI can do, but by what we choose to do with it.
Well said. The power is immense, but so is the responsibility.
Thank you so much for joining us for this deep dive into artificial intelligence. We really hope you walk away with a much clearer, more foundational understanding of this incredibly transformative technology, what it is, how it works, and why it matters.
And what's fascinating here, I think, is that the more we understand these underlying mechanisms and their broader implications, the more informed and impactful our choices can be, both as individuals interacting with these systems every day and as a society shaping their future. It really empowers you to see the world and the technology shaping it a bit differently.
Absolutely. So keep asking questions, keep exploring, keep learning. Continue your own learning journey into this fascinating field.